Good morning. ഈ ലിസ്റ്റ് ഇവിടെ നിന്ന് തുടങ്ങിയാലോ എന്നാ?
Good morning, everyone. Welcome to the auspicious occasion of the Symposium on Nuclear Energy for Sustainable Tomorrow, NEST 2025. We request all the dignitaries, Dr. Vishnu R, Dr. Vijay P.S., Dr. K.K. Surendran, Dr. K. Bhaskaran Pillai, Sree J.D. Metal, Dr. Praveen Kumar, Sri K.P. Vishwanathan, Dr. T.R. Govindan Kuti to grace the dais. I request Arya Mohandas, Physics Association Secretary, to grace the dais. So, once again, welcome to the auspicious occasion on the Symposium on Nuclear Energy for Sustainable Tomorrow, NEST 2025, in association with Indian Nuclear Society INS Mumbai and Atomic Energy Retirees Association ERA, Kerala, being held in the blessed campus of Sree Krishna College, Guruvayur. Sree Krishna College, Guruvayur is a prestigious institution that specializes in arts and sciences. Established in 1964, the college is affiliated with the University of Calicut and is managed by Guruvayur Devasam. Over the years, it has developed into a leading educational institution offering 13 undergraduate programs and 6 postgraduate programs. The Department of Physics and Botany at the college are dedicated research departments. Recently, Sree Krishna College received National Re-Accreditation with an A grade from NAC. The Physics Department at Sree Krishna College has significantly grown and evolved since its establishment in 1964. And in 2015, the department has recognized as a research center by the University of Calicut. The department primarily focuses its research on atmospheric physics and material science. To formally commence this auspicious event, we will begin with a prayer by Meera Ulanad by seeking blessings for the success of our deliberations. Agre pashyami tejo nibitha.
Very good. I would like to extend a warm welcome to Dr. K.K. Surendranathan, the esteemed President of the Atomic Energy Retirees Association. His unwavering dedication and tireless efforts have made this seminar a reality. We are truly grateful for his commitment to our student community and the advancement of discussions on atomic energy. Welcome, sir, to this meeting. We are incredibly fortunate to have the opportunity to associate with Dr. T.R. Govindankutti and Dr. Praveen Kumar, who have been instrumental in making this event a reality. Their commitment to advancing our understanding and practice in the area is truly inspiring. I wholeheartedly welcome Dr. T.R. Govindankutti to this meeting. Welcome, sir. Dr. Praveen Kumar, former scientist at BARC and the alumnus of the department. This event, thank you all.
Thank you, sir. And the next is presidential address to be given by our dear principal, sir, Dr. Vijay P.S. Sir, please.
Good morning. The distinguished dignitaries on the dais, Dr. K. Bhaskar Pillai, renowned medical physicist, and Sri G.D. Mittal, Secretary INS, and Advocate P.V. Vishwanathan, and Dr. K. Surendranathan, President, AERI, and Dr. Praveen Kumar and Govindankutti, Dr. Govindankutti, joint conveners of 2025, student Arya Mohandas, physics, wishing the distinguished guests and other delegates a happy and a comfortable.
About the era, it's my honor to invite Dr. K.K. Surendran
of this institution. On this occasion, I remember with gratitude the continued support and advice we received from several other coordinators also. I again express my sincere gratitude for giving such a great opportunity to our organization. Thank you one and all.
Thank you, sir. Thank you for your words. Now, let's proceed First lighting of Bhadradipam, chanting Agni Nayasupathan. We request Dr. K. Bhaskaran Pillai sir to light the lamp. And now comes the most awaited moment of the day, the inauguration to be done by our chief guest, Dr. K. Bhaskaran Pillai, renowned medical physicist. Born at Chenganur, Kerala, he had his bachelor degree in physics and mathematics in the year 1955. In 1957, he joined the Scientist Training School of BARC. He had his MS in Radiological Science from University of Wisconsin, USA in 1972. He had his ABR certification in therapeutic radiology and physics in 1975, diagnostic and medical nuclear physics in 1977. He had his PhD in biomedical physics from University of Texas, USA in 1980. His career includes 3 phases. Phase 1, 1957 to 1971 at BARC. Phase 2, 1971 to 2003 in USA. Phase 3, 2003 to present in India, the motherland. He was awarded with Colombo Plan Fellow, Australian Atomic Energy Commission Lifetime Achievement Award in Medical Physics in association with AMPI and ISMP USA. Later, he became elected Fellow of the American Association of Physics in Medicine. Let me have the pride in welcoming Dr. K. Bhaskaran Pillai for inauguration and keynote speech. Sir, please.
Hello, everyone. I'm glad to be here, and I want to observe that we are all here because of 2 people, and that is Jawaharlal Nehru, our beloved Prime Minister, and Dr. Homi J. Baba. These 2 individuals had the vision of nuclear energy, nuclear science, nuclear energy, and its role. Not only the nation, but the whole world. I wish to congratulate both of them. Thank you, everyone here, to invite me to give this talk on nuclear energy. Recently, this got a lot of publicity. Let's go back to what we did in India, how we started. We got our first reactor, a swimming pool reactor, just a tank of water. 1 megawatt thermal. It was a great thing to have our own. We built our own. Then we got the Canada-India reactor, 40 megawatt thermal, the big dome that you see. And Tarapur power plant, Kota, Rajasthan power plants, all these are many, many units of the nuclear reactors. Then we got Madras power plant, and we now have one in Kudankulam, and so on. So why is this? We have almost run out of our conventional coal fuel. We are almost run out of it. With the railways also taking most of it, we don't have any power left. And in many parts of India, there is not enough water, so the hydropower is also dwindling. What do we have left? Only nuclear power, and that is plenty. Nuclear power, the little atom, is giving us all the power. We'll come to that. In 28 countries of the United Nations joined together to discuss not this problem of power, but to discuss the problem of greenhouse gases, increasing the temperature of the world much, and without control, that will run amok. And finally they decided they now have a level to work for of the temperature level increase. What temperature can we allow the world to increase to without the deleterious effects? And that has been determined to be 1.5 degrees. So, hence we have this COP28, that is the countries who joined, of countries of the United Nations who joined to discuss the global commitment to triple nuclear energy for a suitable future. Now we suddenly came to energy, nuclear energy, and triple nuclear energy. They have decided to increase the nuclear energy contribution to about 3 times. And that is the triple nuclear energy for a sustainable future. What is sustainable? No deleterious effects. And there is no effects of using fossil fuels. We have now stopped almost using fossil fuels, and it is allowed only up to give not more than 1.5 degree temperature increase. So the imperative to combat climate change
has reached a historic juncture as over 20 countries from diverse corners of the globe converge in a unified commitment net zero greenhouse gas emissions, maintaining the 1.5 degree temperature rise limit, and realizing sustainable development goal. The nations endorsing this declaration include a diverse array of global players such as the United States, Bulgaria, Canada, Czech Republic, and the United Kingdom, among others. As the world grapples with the urgency of addressing climate change, this collective initiative marks a paradigm shift in the approach towards sustainable energy solutions. We cannot quarrel anymore. Hey, we cannot have nuclear fuel because it is dangerous. That is an impression simply carried on by people. Just an impression, but not any reality. It is a reality now that we are going to triple our involvement of nuclear energy. So the nations endorse here and the United States. As the world grapples with the urgency of addressing climate change, this collective initiative marks a paradigm shift in the approach towards sustainable energy solutions. This article, okay, just a minute, okay. This article delves into the key elements of the declaration, unraveling the ambitions, commitments, and collaborative spirit that underpin this monumental effort towards a greener and more resilient future. Introduction. More than 20 countries, as I already indicated, okay, all right. It highlights its role in monitoring climate change and addressing its impact. Already mentioned tripling of nuclear energy capacity, ambitious goal, global aspirations to triple nuclear energy, commitment to collaborative efforts considering each nation's unique circumstance. Not all countries may want to go for nuclear, so depending on the country's unique situations. Offers additional flexibilities supporting decarbonization beyond the power sector. International cooperation and financial support invites shareholders of international institutions to include nuclear energy in lending policies, innovations in financing mechanisms, encouragement for financial support from regional bodies, commitments to responsible nuclear energy, emphasizes responsible operation of nuclear power plants, adherence to high safety, sustainability, security, and non-proliferation standards. These are some of the problems that were faced by the earlier nuclear reactor facilities, but now they have been all controlled, all streamlined. The inclusion of the declaration of triple nuclear energy stands as a beacon to global cooperation and commitment to address the urgent changes posed by climatic change. With more than 20 nations from diverse regions endorsing this initiative, it signals a collective recognition of the pivotal role nuclear energy can play in achieving net zero greenhouse gas emissions and sustaining 1.5-degree temperature rise limit. The commitment to tripling global nuclear energy capacity by 2050 reflects a shared vision for a cleaner and more sustainable future. As these nations pledge to work together, mobilize investments, and encourage responsible nuclear energy practices, the declaration paves the way for a transformative shift in our approach to energy production. It not only emphasizes the importance of international collaboration, but also acknowledges the need for innovation and flexibility in our pursuit of a resilient and low-carbon global energy landscape. The journey towards a sustainable future is underway, driven by the collaborative spirit embodied in the historic declaration. I think that's all I want to say as far as nuclear. What do we do now? We have reactors and we want more reactors, but we cannot have but reactors because the fossil fuel is going down. There is no fossil fuel left, and that is also dangerous. So what is left? The other conventional fossil fuel all dried up. So it is now time we are taking a different step from this. One more thing, difference in technology. Well, until now all reactors were thermal reactors, and they are all fission, splitting the atom, splitting a large atom, we get energy. But fusion gives 100 times or more energy per reaction. The sun, how is the sun burning so far? Fusion. Hydrogen is fused together. So fusion, we now have a fuel thorium. We have about 10% of all thorium, and that means 10% of fusion energy. And that is a different scale of nuclear energy. So I wish to thank the organizers of this for inviting me to talk a little bit about this. A little bit I learned in these years. My main field is medical radiation physics, where you apply radiation for medical purposes, diagnosis or treatment of cancer, and so on. It is different from power. But power is a big scale, and now from fission to fusion, we get plenty of power. No reason why we should not tap it. So let's go for it. That's all I want to say. Thank you for
Thank you, sir, for your insightful words.
any questions? Yeah.
Now it's my privilege to invite Sri J.D. Mithal, Sir, the Secretary of Indian Nuclear Society, INS, to speak on vision and mission of INS.
See, I am J.D. Mittal, Secretary Indian Nuclear Society. First of all, I show my welcome and gratitude to Dr. P.S. Vijay, Principal of this college, for having agreed to arrange this function, sir. And my colleagues from Atomic Energy Retiree Association Kerala and my colleagues also they are there in Indian Nuclear Society. I don't want to take too much time naming individuals, but I see in my audience those my colleagues from, I don't want to name, so many are there, but from young generation, Dr. R. Tiwari and Mukti Ranjan Rai, who are still working, and my recently retired Sree Malhotra. He will be talking, and then I want to curtail because he has to rush to catch the flight immediately after lunch or maybe before lunch. So I want to emphasize on one point. My young colleagues are sitting, they are thinking what benefit it is going to come to them by this conference. How many of you have seen the X-ray done of any part, body part? Have you seen X-ray done? Raise your hands. X-ray. No, none of the young fellows know the X-ray. See, okay, how many are aware of angioplasty or angiography? Your elders must be knowing that some time or other you get angiography done for your seniors and you get the treatment done. Have you ever worried that it all involves radiation? Everybody knows that this is beneficial, so we accept this as a routine thing. Then, when reactor, we say power generation, there is a big reactor, so much thorium, neutron, this terminology is very great. But when it comes to beneficence of the energy and terminology used, we just don't bother. As far as it is helping me, I don't care what is radiation. So, people are little worried about the word radiation, but the moment it comes to my benefit, I just ignore that. So, this is not just for young or old. A common person feels that radiation is very dangerous and we should be careful. Sometime, maybe 35 years back, our great scientists of that time, including Dr. Chidambaram, Dr. Kakodkar, P.K. Iyengar, etc., Dr. M.R. Srinivasan, they thought of clearing their doubts in the knowledgeable person. I am not saying those who are not aware. Problem is of knowledgeable person. Like you students, you are sitting here, you may have so many doubts. What is this radiation? While we are talking of nuclear, so we formed an association that I will be talking separately. Right now, I say nuclear energy is just source of generating steam which is used to run the turbine. As long as you are able to run the turbine, power generation will be there, whether you use it by wind or steam or by any other means or hydro. Now question is forming the steam, whether you burn by coal or gas or there is some other thing. And that some other thing when we talk about nuclear is by generating heat to make the steam by nuclear reaction. So forget about that part. Somebody else is doing and it is very safe. So nuclear power can be generated simple way. Now I don't want to take much of time. I just say that my young students, my friends, don't have any fear of any kind as long as you are getting masala dosa in your kitchen, you are happy. You are not worried how your mother is making it. Simply accept it and leave it to others, those who know. Just remove your doubts. And if any doubt is there, talk with the knowledgeable person and not with unknown person who doesn't know anything. Thank you very much.
Thank you, sir. Thank you for your inspiring speech. To give us a glimpse into the symposium's agenda, I invite Dr. Praveen Kumar, the Joint Convener, NEST 2025.
Distinguished scientists on the dais, faculty of Sree Krishna College, where I was a student about 50 years back, and my colleagues from atomic energy who are in the front rows here, and delegates. Thank you for giving me the opportunity to be here. I am given the responsibility to talk about the need of this such a symposium. In fact, we are all retirees of atomic energy, and we used to conduct these awareness symposiums in many colleges. UC College, we had conducted one in St. Thomas College. So this is just to, the need of this symposium is threefold basically. One is to understand what exactly is nuclear energy, and in Kerala especially there are so many apprehensions about nuclear energy because of the accidents happened earlier. So we would like to clear the apprehensions and misunderstandings about the nuclear energy and get a clear picture of challenges and risks. It is not full of challenges only, it is with challenges and risks. No technology is coming without risks. And what are the advantages of nuclear energy? In India, we use 3% of the total power production by nuclear energy, whereas in worldwide it is about 9%. And compare that to 22% of the hydroelectric power generation and about 65% from the conventional thermal power plants. This nuclear energy has got the advantage that it has got the very low carbon footprint. That is, carbon emission is much low while running a reactor, and eliminates extensive use of fossil fuels. And fossil fuels, they take many centuries to get created. And if we use it within about 40 years or 50 years, fossil fuel won't be available for future generations. And there is, though installation cost is higher, running cost is much lower for a nuclear installation. And India is gifted with high
amount of thorium deposits. So thorium-based reactors, we can think about that in the future, which have got an edge over other countries in this world. And what are the applications of nuclear energy? Many people, as Dr. Mittal has suggested, many people would have undergone the benefits of nuclear energy, power generation, nuclear fission and fusion technologies, radiological safety aspects and environmental issues, accelerator technologies and nuclear medicine, heavy water waste management and rare earths, nuclear applications in biology and agriculture, and things like that. And these talks will be done by the experts in each of these fields. And we get an opportunity during this seminar to have an interaction with them, maybe a close level of interactions during tea, during lunch and all those things. And for 2 days they will be with us, and we have to maximum utilize their proximity, and we can discuss about, we can clear about the apprehensions, we can have opportunity of interactions at a close level, and we can discuss about career opportunities in atomic energy, and we have got a special interactive session with the students also, where they can raise their doubts, and the experts in that field will clear their doubts. So I hope that delegates will make full utilization of this 2-day seminar, and they will raise a lot of doubts. They will get clear idea about nuclear energy, and if that is done, this seminar I find it successful. Thank you.
Thank you, sir, for your words. Next, we move on to the felicitation segment. For that, with equal pleasure, I invite Arya Mohandas, Secretary of Physics Association, to convey the felicitation.
Good morning all esteemed dignitaries, distinguished scientists, engineers, faculty members and dear students. It is an immense honor to stand before you today at the prestigious National Symposium on Nuclear Energy for Sustainable Development hosted by Indian Nuclear Society and Atomic Energy Retirees Association at our Sri Krishna College. As you all know that nuclear energy stands as a pillar of hope in our pursuit of energy security and environment sustainability. With its potential to provide large-scale, low-carbon power, it plays a crucial role in reducing our dependence on fossil fuels. The expertise and dedication of these scientists and engineers present here have been instrumental in advancing India's nuclear technology, ensuring both safety and efficiency in its applications. On behalf of our Sri Krishna College Union and Physics Association, I extend my heartfelt gratitude to the brilliant minds who have joined us today. Your research, innovation and commitment continue to inspire young minds and pave the way for a self-reliant and sustainable India. Once again, I extend my warmest felicitations and best wishes for success of this symposium. Thank you.
Thank you, Arya. Now, for the vote of thanks, I invite Dr. T.R. Govindan, Joint Convener, NEST 2025.
Good morning, sir. Good morning to everybody. As we conclude this inaugural function, it is my pleasure to extend a heartfelt vote of thanks to those who made this event possible. First and foremost, I would like to express my deepest gratitude to our esteemed guest, Dr. Bhaskaran Pillai, for gracing this occasion. Your inspiring words set a perfect tone for this symposium, sir. I had met Dr. Bhaskaran Pillai 3 months ago at Chairpur when there was a symposium in honoring Dr. Bhaskaran Pillai. I happened to talk to him at that time and was really impressed by the way, the knowledge he has. Your presence today is a testament for your commitment towards science. I would like to thank Mrs. Bhaskaran Pillai for bringing him to our audience to this conference. Now I would like to extend my sincere thanks to Sri Krishna College for helping us to organize this symposium. I would like to profusely thank members of the Guruvayur Devasam Board, especially their chairman,
Professor Vijayan, who was given us so many valuable insights. We would like to thank Sri K.P. Vishwanathan, who is a member of Devasam Board, who is always helping us whenever we requested for. Our college principal, Guruvayur Devasam Sri Krishna College principal, Sri P.S. Vijay, who stood behind like a rock and helped us whenever we are in doubt. Now I would like to thank Sri J.D. Mittal, my ex-colleague, my friend, my guru and my guide. He was very helpful in helping us in a crucial juncture. He did everything that he had promised. I would like to extend my heartfelt thanks to him and to also the INS Executive Committee, especially to President of INS, Dr. Jagtap, and members like KTP Balakrishnan and Dr. S. Gangotra. Our founder President K.K. Surendranathan, under his leadership, this program is taking place, is always helpful. And I am deeply indebted to Sri K.V. Das, Vice President, who is sitting in front of me, who is making the end, Sri K.K.P. Nair, our Secretary, who made this symposium possible as a great event. My colleague and co-chairman, Dr. Praveer Kumar, is always proactive and leading us from the front. His wisdom and guidance for the symposium was very helpful. And finally, the man of the match is Dr. R. Vishnu. He is sitting behind. He is our convener. I have no way to describe his contribution. Without him, this was not possible. And he made it possible due to his hard work. We used to communicate on an hourly basis. And he used to inquire about everything. And I am especially thankful to him. Thanks to Dr. Vishnu. We have great speakers from DAE. We have got 6 speakers from DAE. I would like to thank every one of them for coming and giving their lectures. First, I want to thank Dr. R. Tiwari. He is my friend. He is a distinguished scientist and director of Materials Group. Despite his having a very heavy program, he has committed to us and he promised he will come and he has already come. We are already here. Also, my sincere thanks to Sri Bhaktasi, who was not come, Anand Gangadharan, Sri M. K. Ray, who is already here, and G. Haridasan, Dr. G. Haridasan is already here, and R. V. Vishwanath. Vishwanath, I don't know, he has come. For their presence, despite their heavy schedule. Now I would like to thank our retired senior scientist, Sri Dr. S. V. Jiman is already here. Menon is a distinguished scientist, former director of physics group, and I am very much thankful to you. And I also would like to thank Dr. S.K. Malhotra, who was an outstanding scientist and former head of public awareness program in BRC. Thank you, Dr. Malhotra ji, for coming and giving a lecture here. I would like to thank further Dr. M.R. Iyer, although he has not come, he used to call me each and every day and inquire about the symposium. Although he is not coming, his paper will be presented by his student Dr. P.M. Ravi, who is also an expert in radiation technology. Now I would like to thank Sri M. Bhaskaran, former Chief Executive of the Board. I think he is already here. I would like to thank him for his commitment and for coming and giving a lecture here. My friend Dr. K.N.S. is here and he is going to give a talk on his great work he has done in Cochin. I thank you, Dr. K.N.S. for coming and for giving the talk. Further, my thanks to University Professor Dr. Imam Mustafa and Dr. Praveer Kumar, who is coming from QSAT, for their valuable help. Now I would like to thank all the members of AERA, who has come for the symposium. I am personally thankful to Managing Committee and members of the awareness program for the intense support for making this event possible. I would like to acknowledge people who was given financial assistance for this symposium. My special thanks to INS for the generous contribution, financial contribution. I would like to thank molecular cyclotron, Mr. K.N.S. is already here, and Dr. Ambi Pillai for the help. Further, I would like to thank to IRL Kochi and especially Sri R. V. Vishwanathan, Chief General Manager for the financial assistance. I would like to thank to press people for arranging a press conference and who has come to attend this symposium. Finally, I would like to thank to all delegates who have come from the various colleges of Kerala. I request them to participate in the entire activities, today program, and to raise question whenever you are in doubt. Asking questions is the dharma of a student. That's what I feel. So whenever you are in doubt, please ask question. As my co-conveners already told, we are planning to have a close interaction between the scientists of Department of Atomic Energy and you people. So please take this opportunity. It's a great event. We cannot get such an opportunity in the future. Further, I would like to thank faculty members of Guruvayur Sri Krishna College, especially the physics department, for their valuable help. Also, a big thanks to the supporting staff and technical staff for their behind-the-scenes efforts for ensuring the smooth running of this event. Thank you for everyone for being a part of this symposium. We look forward to a successful and engaging symposium ahead. Thank you very much. Thank you.
Thank you, sir. With that, we conclude this inauguration ceremony of NEST 2025. We will now have a short tea break. We have arranged high tea outside the auditorium. All are requested to have the tea and gather here in 10 minutes so that we can proceed with the technical sessions. Thank you. request all of you to gather into the auditorium and to be seated. The session is about to start. Welcome back everyone. Hope you enjoyed the tea break. We are now moving on to the session 1, which will focus on the advantages and challenges of nuclear power generation. We encourage you all to participate actively and engage in the discussions. We wish you all a fruitful and enriching symposium. We have two distinguished speakers for this session. First, we have Dr. Raghavendra Tiwari, Distinguished Scientist and Director, Materials Group, BAUT, who will be speaking on energy scenario in the country and changing role of nuclear energy in India. Following him, we have Sree S.K. Malhotra, Senior Scientist, BAUT, retired, former Head, Public Awareness Division, DAE, who will be speaking on achieving net zero targets of India in the inevitable role of nuclear power. The session will be chaired by Dr. S.V.G. Menon, former Distinguished Scientist and Group Director, retired, BARC, Mumbai, and co-chaired by Dr. Nishant T., Assistant Professor, Department of Physics, Sri Krishna College, Guruvayur.
Friends,
for introducing the speakers and chairman of this session, let me invite Dr. Nishant T. Over to you, sir.
Friends, very good morning to all of you. Now, this is the beginning of the technical section, and the first talk is by my old friend Tiwari. He will talk about nuclear power and challenges and what we can achieve and what are the problems which we have to face to go through this endeavor. And I invite Dr. Tiwari to give his speech. But before he begins his speech, my friend co-chairman will read out his biodata so that you have a good idea about what he is working on and what is his background. Please.
Thank you, sir. Thank you very much. So before going to introduce the speaker, just I wish to introduce the brief description about the chairman of this session. We have S.V.G. Menon. who completed post-graduation in physics in 1971 from University of Kerala and moved to Baba Atomic Research Center, joined the theoretical physics division in 1972 as a scientific officer. His research work has been theoretical, mathematical and computational nature, which were needed for different applications of nuclear energy in civilians as well as strategic area. He led the theoretical physics division at BARC during 2002 to 2011 and provided guidance in modeling, design and analysis of experiments in fusion and fission physics. 7 colleagues did PhD work in topics in atomic physics of defense and hot plasma, high pressure equation of state of materials, high temperature opacity of materials, and hydrodynamics and shock wave phenomena. Based on lectures at Theoretical Physics Division, he wrote a monograph titled Renormalization Group Theory of Critical Phenomena. He authored and co-authored around 75 papers in international journals and similar number of unpublished reports on his work in strategic areas. He has received PhD in Applied Mathematics for the thesis entitled Application of Fourier Transform Methods to Resonance Absorption Phenomena in Nuclear Reaction from Bombay University in the year 1978. He taught, he is an eminent personality in handling the topics such as reactor physics, statistical mechanics and mathematical physics in the training division. He retired as a distinguished scientist on 31 October 2011 from BARC and however continues research work. These are a brief description about the chairman of this session, SVG Menon, and now I wish to introduce the first speaker of this session, Raghavendra Tiwari, who is the distinguished scientist and director of Materials Group and senior professor of Homi Bhabha National Institute. His field of specialization mainly comprises of physical metallurgy, refractory metal alloys, transmission electron microscope, materials for nuclear reactors, etc. Dr. Raghavendra Tiwari, whose structural materials for generation for reactors, molten salt breeder reactors, have been developed for his extensive research work. For his fusion reactors, he has developed a lead-lithium-based eutectic alloys as a coolant material. He is an instrumental in developing first indigenous scanning electron microscope for the country and installation and usage of first probe corrected microscope in India. He is currently the president of Electron Microscope Society of India. He has the recipient of Rolls-Royce Research Fellowship in the year 2003 and 4 from the University of Cincinnati, US, and SRC Fellowship from Department of Atomic Energy, and the Fellowship of Electron Microscopy Society from EMSI in the year 2014, and the Fellowship of Indian Academy of Energies in quite recently 2024. He around 261 technical papers are in his credit, and 8 book chapters and 4 patent is also he's having. With immense pleasure, I would like to invite Raghavendra Tiwari for his presentation in this session.
Thank you very much. At the outset, I want to say first to Dr. Kutti, for almost, though he looks lighter, but he sat on me very heavy so that I should come here. Actually, there was some other commitment, so I had to drop that off to come here. But it's always good to come God's own country. And morning he sort of made the arrangement to meet with the God also. So thank you very much, Dr. Vijay, Principal, for doing the all organization and inviting us for all these things. Basically, today, in the beginning, generally I'm more acquainted with the very strong technical presentation. So I was trying to go slow on that. So whenever you feel it's going too technical, just raise hand, I will switch over to the mood. Okay. With that, I just wanted to give you the changing scenario. So you must have heard and aware of what is happening. So I just wanted to give you a very short glimpse of this, that currently India with a large economy, that is economy more than $1 trillion, is growing at a pace of 7% growth rate, GDP. This is one of the highest, with China competing sometime up, sometime down, is the highest growing rate. And such is strong that our growth rate is not slow, but the baseline is increasing, so your rate appears slow. So 10 divided by 100 will be something like 10%. But 10 divided by 200 will look like a 5%. So that is the problem. So in this, what we required is the side is that we required electricity. If you see over here, on that, I think this laser is very weak here, but you can see on the left side, the last 7-8 years our electrical demand was very, very meager and slow. The rate is very slow. But next 7 years, we are going to ask for the electricity or energy in total in the exponential forms. And that is, energy has to be supplied by one way or other. So I just wanted to give you a very small scenario to you, that in next up to 2040, our energy requirement will jump minimum 3%. This is the most conservative figure given by the Government of India, this Niti Aayog. Now, the second problem is, even if you look in that, our electricity demand will go 5 times. If you want to sustain this growth, we have to produce 5 times more electricity what we are doing today. Now, this energy is not coming cheap. What we are doing is we are burning hydrocarbons in various forms, gas, petrol, coal and other form. And this energy production generally is based on the imports, coming coal from Australia and now oil from the Russia and other parts of the countries. And this is creating problem because current situation is, and you know the political economic situation of the country, if the dollar become costlier by 1 rupee, it will drill a hole of nearly $270 million in your pocket. If the barrel becomes $1 costlier than current price, it will drill another hole of $220 to $230 million. So together if they take place, which is not an unseen scenario in the current scenario, this part, we will drill nearly $500 million drill hole just by importing petrol. So you can think of this is more than the economy of the nearly half of the country of this girl, which we are going to blow in the petrol. So this is the problem. And the situation is not going to improve. As we go for more and more progress, we will demand very, very large amount of the energy on that. The worst scenario came in 2023 December, when on one payment, single payment was a $10 billion by the Government of India. After that, thanks to Russian-Ukraine war, we started getting some cheaper substitute. Otherwise, this figure could have gone to 15 or 20. So this scenario is not going to place everywhere, so we have to work on that. So what is happening, what is happening is that in this, with this growth, by 2035, we will be demanding 10% of the electricity produced in the world. This scenario is going to go from bad to worse. Now further complication starts from the fact, just I wanted to give you the sort of a perspective of the scenario. In 2014, we were producing 800 kilowatt per electricity unit per person, per capita, the capital of the country. We were standing on the 99th rank. 15 years, we increased our capacity to 1200 only. We reached to the 3rd position by 2021. But this electricity itself is the 1/3 of the world average. Suppose we want to meet the world average, we'll be standing on the top with second person producing half the electricity what we were going to produce. So with this scenario, how to go about? The situation is not very, very conducive in the way that most of the electricity what we are producing is by burning fissile fuel, and in that coal. 80 to 90% electricity is still coming by the coal. Now the plant I am showing you is the Singrauli plant, which is one of the finest coal-fired plant by the NTPC, where electrostatic catcher, there are some carbon catcher, everything is introduced. But you can see the haze around the plant. It is having carbon dioxide, it is having carbon monoxide, vapors, many hydrocarbons, suspended particles put together. If we increase this, multiply 3 times in this side, then how the country production will be going from the haywire. Health will go on. People have become, they live longer, but the healthy life has become shorter. At the age of 25, you start getting heart attacks nowadays. Okay, so cancer is started striking at as early as 18 years old. Old time, people were living 60 years, but 58 years were healthy. So situation has not improved. Your age has increased in number, but the quality of age has come down in fact. So we have to work on these points. This is the basic introduction I wanted to give over here. Now, the scenario is not going from bad to worse. Why? There is a paradoxical situation. Paradoxical situation is government, the first, Dr. Manmohan Singh's government, they said that don't worry, though the electric production will increase, we will cut down the carbon footprint by 21st century to the same as it was 2000 years ago. So 100 years our carbon footprint come before. But the current government is over-aggressive government. And what they said, by 2070, they will remove the footprint of carbon from the country. Now, this situation, when it started coming up, we have to really think whether we can do it or not. Now, if you started sitting on that chalkboard, started working on that, you will find that you don't have too many options available to the country. So, we started working on that. This is the one chart which has been presented in almost every parliament of the world. So, I am just showing a gist of that. See, if you look on the left side is the carbon dioxide. So, if you are burning coal, nearly 800 gram per kilowatt energy carbon dioxide you are releasing to the atmosphere. Okay, if you come down to the gas, it is reducing a bit, but not much. The short-term solution is that develop devices which capture carbon and store it. Okay, so in this process, you are not, the carbon is not wasted into the atmosphere, but will become available to you for the next cycle of the fuel. And as a consequence, average carbon dioxide level comes down. That is the one thing. That's why electrostatic catcher and everything are being put. But it is not, even in the, now government of India started putting that on every vehicle you should have a Bharat Code 2, Bharat Code 3. They all have carbon catchers so that they can catch carbon and reduce the carbon load on the atmosphere. Now the second problem comes in is that we have to look on the right side where you have this power, solar power, hydropowers and nuclear power, where carbon production is almost next to zero. Actually, carbon is produced to make this material. While functioning, they are not producing carbon. So whatever little side you say is used while, for example, silicon crystal required heat. To generate this heat, you have to burn carbon dioxide, carbon. That is the way some part is shown over here. Now, government India has gone left and right center and started asking everybody to produce electricity, solar electricity. Solar electricity is a very good solution for the things. Okay, but it has an issue. The problem is the maximum electricity demand comes when sun goes down. Suppose 6 o'clock is the sunset time, up to 8 o'clock is the peak power. At that time, solar power does not supply any energy. So whatever electricity you produce, you have to store it so that you can make it supply on that. Second issue is the PV supply, that is photovoltaic supply, are DC in nature. So you have to convert into AC to transmission. And that is a least efficient process because 30% electricity goes waste. So a new terminology is coming up, installed capacity and production capacity. and fluctuations. So far, technology is not there to see the fluctuation into the materials. Okay, so with this idea, we people started thinking little more on that. So that's why one of the largest solar electricity plant is in Karnataka, which you can even map from the Google map. You can see that. If you see in this plant, a small town, a small village in the center with the white spot. This is the whole city. So much is the large is the plant. And so you require this much of the land. Where is the land? We are the country of 140 billion population, 1.4 billion populations going on, 140 crore. Where will we have the land? Whatever land was there is already being consumed by every person. So this is the one of the power of the solar energy. Then the second better solution is the wind power. Wind power is more stable, runs throughout the year, throughout the time, but again there is a fluctuation in the wind pattern. There is sometimes too much of wind is there when cyclone is moving around, or sometimes it is standing still. Again fluctuation starts. The worst problem you have to, in order to increase the efficiency of the plant, you have to use rare earth magnets. Rare earth magnets only one country produces, that is China. And the moment they find that you started making too many windmills, they will stop the supply to you. So before ensuring this solar wind power, you have to find a way to make the hard magnets. What Chinese did, they dropped the price of the rare earth so low that all the American companies they wiped out. All the Japanese companies they were wiped out. Now they are ruling the roost because they are the only supplier in the world. So you have to fight this process because I am sensitizing you the complications. So what happened that later on the discussion took place. Now probably Power Ministry is coming out, Government of India is coming out a separate department called Department of Energy, DOE, to cater this need or to mitigate this problem. Yeah. See, now, if you combine these two, wind and solar, you have two problems. One, you can see the wind pattern is not uniform across the country. It is tilted towards the west side of the country, where you have lot of wind because of the monsoon coming and leaving, they generate. Now, if you superimpose solar power on that, then solar power is also tilted towards the west. So they are not complementing each other. They are competing with each other. You can use the same space either for producing wind or for producing electricity. So the total area of the country is still can be divided into half. So half the country has to produce and cater the whole country. This will create a lot of disparity into the system. So you have to find out. That's why another approach being taken up is that let us combine everything. Solar, wind and nuclear. The advantage is nuclear energy is a very condensed form of energy. The same power if you require for production of electricity, so you will find that in case of nuclear, you require only 2 square kilometers. Same electricity you want to go with this solar energy, you require 400 square kilometers. With wind further up. So how to mix all this form energy, because our demand is going to be so high that there is no point to compete. Wherever any farm you get electricity, you try to produce it. Because in nuclear site, what happens that we, as per the norm, I think the next speaker is going to speak more on that, is required as a exclusion zone. So in the exclusion zone, why don't put all these things where no human can stay? So where we put electricity and all these things so that all the time can be done. Now idea is solar power is fluctuating power, the wind power is a fluctuating power, but nuclear is a very stable power. So in what happens that you draw a baseline and then keep increasing power on that. That is the basic idea. And that is why the energy concept changing. But scenarios is changing very fast. These planning, before that you come up with the plan, our demands are changing. Sorry. just wanted to give you very glimpse because the students are there and how the nuclear energy is produced. You know that in the case of nuclear energy, God has given only one atom, which can be converted, split by the insertion of neutron, that is uranium-235. And that exists in the uranium only 0.7%. Rest we had to produce. So there are two concepts, fissile and fertile. In the case of fertile elements, you forcefully give one neutron to the element and then allow it to adjust itself so that it becomes fissile. That is the approach. Now thorium, we have one of the largest thorium thanks to a very large sea coastal line, but they have thorium. Thorium cannot directly be used. You have to cook it to make it a fuel for yourself. And that is where these two neutron isotopes are given. And the first person who realized this effect was the Bhabha, who said that we have so much of the potential fuel available, why not try for that? And there were issues there because the country was nascent. See, he was thinking of plutonium, but the average Indian was thinking of the bread. So this was the separation between the two lifestyle of the India. And that is why our first generation gone in securing the bread at the table. Now the time slowly is coming up, everybody is rich enough to think about all this plan. Before that we were struggling, every day was a struggle. So this is the point I wanted to tell you that. Now he came out with this idea that generally rest of the world were using, you take the fuel, put inside the reactor, use as much as possible, then dump inside the depositories. That is in the Nevada depository Americans are doing. But in India we do not have such kind of luxury. So what we have to do, that's what Indians do. That when you have if you see in the house, when they have a new cloth, they wear outside. When it warms a bit, they started wearing inside the house. If it goes further, they use it for mopping the floor. Till each thread is broken, they keep using the thing. This is the Indian mindset. That is the way it has been designed. That is the 3-stage program India has proposed. Okay, so here you put in one reactor, take the waste of the material, find out what is the good value, take it up, and then use it. This has given us two edges over the rest of the world. First of all, many isotopes which were thought to be very, very, very useless, becoming useful for us. And for many cancer therapy, they are being used. Now we are the only country in the world who are producing 35 different isotopes for the medical isotopes for various applications. Now many countries, we have advantage. For example, yttrium, if you put inside the reactor, it gives the beta. Now person is having liver cancer and is in the last stage of dying. You can inject these yttrium-based sphere and it will kill all the cell what it sees. Since liver is contained by 90% cancer cell, so 90% cell will be dying with the cancer cells. So as a process, we have done this experiment successfully. Now our Dhruva reactor constantly supplies this to different world. Now this dose when used to come from America used to cost 40 lakhs. And by the time it used to reach to the hospital, 5 life cycles were over. So it has become very benign kind of the medicine. Now what we do is, based on demand, we take the material out of the reactor, immediately sent to the hospital. And cost is only 20,000. And 20,000 is only because doctors said that if you give free, people will not value it. We wanted to give it free. Okay. Now if you inject, the person who has a 7 days life, the person on him, if once it was injected, now 8 months have passed, he is still alive. So there are the positive effect of the isotope, which probably you do not know that part. Now lutetium is another one which we are trying very hard to give the dose and let the person live the normal life. You will never know that he has a cancer. These are some advantage of the radioactivity. So these 3 programs were proposed by Bhabha. Now second program is just about to finish because PFBR entire core is loaded. Now we are waiting for ARB's licensing for the certain experiment to be done because without that we cannot do it. So within 1 year time probably the reactor will start doing the experiments of producing electricity from plutonium. This has the largest inventory of sodium on earth. our production will be the largest in the world. Countries like Russia has small reactors. France, even US are keeping an eye on that. So when the negotiations of the nuclear policy were taking up 1, 2, 3, they were eyeing on this. They wanted a direct access to that. And that is where the maximum fight took place. Now, this is what happens when you take the reactor, put inside the, take it out. It is very hot. As compared to the average natural atom, it is having nearly 10 to power 8 times radiation. But when you take 10 to power 8 reaction and start taking elements out, if suppose 10 to power 8 dose it has and you bury under the ground, it will take nearly 2 lakh years. 2 lakh years means if you go back on the history, the modern humans have not born 2 lakh years ago. They were Homo sapiens only. So 2 lakh years is such a large time. So if we keep removing these radioactivity, we can bring it down to 300. Now, cesium pencils are available for the blood irradiation so that any pathogenics can be killed. Whereas this ruthenium, this is taken out from is used for the eye cancer. So we are taking value out of the waste because of this approach. Then let us move out further on the material. The demand is changing. What demand is changing? They are telling that forget about petrol. We all want electric vehicles. Everybody is running for electric vehicles. Okay. Electric vehicles everybody wants. So in electric vehicles, what you require? More electricity. The petrol which was available has gone, now electricity. Now how to meet those things? So what is happening? Another concept coming up is the hydrogen production. How to produce hydrogen? There are many ways to produce it. Now the problem is we started working more on the new reactors. There are many concepts being started. Idea is that use the high temperature so that you can use for the energy, for the hydrogen splitting. You can use energy, make a smaller reactor to produce same amount of energy and use thorium. These are the 3 goals of that. So I will go fast on this, and these reactors are not new. They were keep coming on and off this thing because once when the petrol was too much of a crisis, American wanted to run the plate on nuclear reactor, and one plane flew on the nuclear reactor, but then they stopped it. Okay, so these high temperature reactor have their high efficiency. That was the one thing. The only problem is materials are too exotic to be developed. That is where the struggle starts. And these are the 6 propositions of the fast coming reactors are there. One is this thing, gas cooled reactor, molten salt reactor. These we are pursuing in BRC. The very high temperature gas cooled reactor we are pursuing in BRC. Then supercritical water cooled reactor, molten salt reactor and sodium fast reactor, these are being pursued by IGCAR. That's the way the scenario goes on that. And I will just give you one glimpse. Molten salt reactor, why it is important. To make you understand, molten salt requires the fluorides of the combination of salts. The entire fuel, this fuel is in the liquid state. Okay. Now this advantage is as when your fuel is in the liquid state, you can tap it out and in as and when you want. You can always manipulate the chemistry of the fuel as and when you want. Why it is required? Just give me 1 second, I'll explain you. Second advantage is it is inherent safe. Suppose reaction started increasing temperature. See, current set of reactors, what they work is they work on the accelerator and brake. That you accelerate to move the car fast, and then you find anything, you apply the brake. By chance, instead of brake, you apply the accelerator. There should be disaster. Now, current reactors, this was the scenario. Anything happens, Chernobyl accident happened because the brake did not work. That is why Chernobyl taken. It's not that reactor was bad. See, this kind of human-related issue can be addressed. In this case, what happens? It is inherently safe. Why? Because if the temperature increases, the salt temperature will increase, it will drain the salt out, and you will have safe on that. Okay? So, so in this process, what happens? That the reason is, if you are wanted to use thorium, you allow one neutron to go, it will become protactinium. And this protactinium this protactinium will, the 233, Pa233, if you take it out, then what happens that it converts into uranium-233 and is useful for you. But you keep inside the reactor, then if protactinium-233 can take 9 neutron and it will become protactinium-234. Now, protactinium-234 will become uranium-234. I have two losses. I lost neutron, I lost a fertile. So it's a double loss for us, one. Second, uranium-234 many times converts into bismuth and all. And they become very strong gamma emitter. And that is why third stage program in India was not taken up so far very strongly, because we had to find a solution for that. So this is the solution for that. So we started to build up the new reactor in the BRC Vizag plant. See, we wanted to start in Kerala. So this was till in the morning. But Kerala government outright refused it. So we have gone to Vizag now to start this plant. So now after this, there are many other. The last set of things where fusion was telling, our professor was telling about the fusion reactor, we are trying for that. Fusion reactor has advantage. First of all, how you do is that lighter element, that you deuterium and tritium mix, and it gives energy. 80% energy goes in the with the neutron, 20% with the helium atom. So you are using. Advantage is very large amount of energy can be released, and in this, just I wanted to give you the perspective. If you go, that your laptop battery can give you your energy demand of the lifetime. This is the kind of electricity you can produce with the fusion. But controlling fusion is difficult. Why? Because the amount of energy reduced and amount of the high energy neutrons come out are very difficult to handle. And that is where the problem starts. And that is where you have struggles. So, if you want to use this material, tritium has to be used. Now, tritium is not there in the world. The rest of the tritium is available in the world. If we want to run one reactor, will be consumed in this within 1 year. So, you have to constantly produce tritium. That is why we started using lithium. Now, the problem was lithium was very difficult to introduce into the lead. So at that time people tried very things. In BRC we tried, and we are the only country in the world who can produce lead lithium alloy for this. Rather, we are the people who supply to France in the Cadresh, where these experiments are going on. And we have floated this company also. The one company has shown interest, it has been given to them. And now this is the Cadresh where this has been used, where 7 different countries are supporting. We are also supporting fusion reactor program there, and you can see that the Indian flag is shining in the middle, and now they wanted to make it 2035, but the complex of technology is so much that now they are pushing it further. Probably in my lifetime I may not be able to see also. People sitting in the young side may see the fusion reactor, because fusion technology is difficult to handle. Okay, now regarding the materials, I'll just take 2 minutes. Just 2 minutes, I'll finish. Okay. So because when we are talking about is the solar power, electric power, this power, we required materials. And we were not having God was not very kind to us in terms of the materials. I just wanted to give you a very quick glimpse of what is happening. That now Government of India has identified many critical elements in the periodic table. Almost how the periodic table has been mapped. And the critical minimum now we define as per the Government of India by these 4 factors. Let us not go detail into that. The point I wanted to tell that these materials on earth are in India, because we had a hot climate, we had a lot of volcanic activity, and we have a lot of rain. These 3 are very dangerous for the concentrated form of ore. Our ores have traveled from one end to another end, millions of years it had traveled millions of miles. So you will never get concentrated ores. Your ores are very lean ore in the entire country. And that is one of the problems. You have to develop a totally different technology. What rest of the world throws out as a uranium waste, we start our uranium extraction from that point, or rather below than that. 130 ppm. Means 1 million particle if you take, 136 particle of uranium will be there. From there we build up the uranium reactor and still make it economically viable. Canadian, if you look, Canadian are so rich that what tailing they throw is 3 times of our ore richness is there. Because the wind, high temperature, flood, earthquake has distributed uranium all across the world. Okay, so is story about other materials. I don't want to go into detail. This is the simple pattern where how our materials are distributed across. So how different our materials group get involved, and we have worked on almost every element now. We are tracing on the very, very footprint of the anywhere, any sources there, AMD reaches there. We have the largest custodian of the knowledge about the different minerals produced in the country, wherever they are located. And for example, beryllium, we are the only group in India which is producing beryllium. Recently, 1st January, this Paris satellite was sent. This is the only satellite which can capture one particular form of gamma rays for the neutron star measurement. So this was made, entire core was made, of beryllium was made by us. I just want to give glimpses of this. This is such a heavy, production technology, very difficult to make. Beryllium is very poisonous. You have to do in containment. It cannot be done in private, and that is the problem. So beryllium, though looks very attractive, doesn't work. Lithium, everybody talks about lithium. Government announced that in this Jammu Kashmir they found lithium. Everybody clapping it. How much? When you ask this question, then there is no answer. More than what Jammu Kashmir has lithium, I think Kerala beaches will be having much better concentration of that. But here it has never been explored, because lithium dissolved in the sea over the years, centuries of years, has been deposited here. Okay, now the lithium demand is increasing, and again you can see the only country which has control is China. We have to quickly make it up, and that is why we are going to set up a plant, new lithium make plant in the India. Zirconium is another one where again the monazite sand gives all the information. And then the rare earth, which is I was telling in the beginning. In the beginning, the rare earth gives you a lot of information, and almost it is sitting in your beach sand everywhere, from all the way top from this thing, for Malabar coastal upline all the way to go to Kanyakumari. This is full rich in that. But we are still have not exploited completely on that. And this, let us forget about science, and I wanted to tell you that, see, now slowly we started doing it. Now one plant has been set up with respect to IRL on the gadolinium ions, and then we are looking in the secondary ion. Just to give an example, that our hard disk, India is the largest importer of computers. What Chinese did, they will, when you destroy the computer, they take the hard disk and pay the vendor, and then that is recirculated back to you with double the cost. So we are trying to intervene, we are trying to get it, this export of this hard disk stopped, so that we can make these materials inside the country. And that is where a lot of struggle started. In Bhopal, we set up the plant. So I just wanted to give you a couple of plants. This plant has been started in Vizag of making the rare earth magnets, and then this is the Bhopal plant, which is making rare earth magnets again for the different material from the hard disk and all. So this has been recently set up. This was March 24 Prime Minister inaugurated. This is yet to be inaugurated. We are waiting for his date. And there are many other, but I think I will stop over here because the story is slightly long. Okay. Because you are running short of time and Dr. Saab, he has to go. So I wanted to say a few more things, but just I'll give you one small glimpse that we don't have nickel, we don't have cobalt, we don't have moly we have, but not well. So now recently we set up a plant. We take junk of the Midhani and try to extract this material for us. So what we have, with the help of heavy water plant, we have set up a plant in the heavy water research lab. So now this plant will produce the demand for the nickel and cobalt into the country. There are many other we started in the future. We started doing from the sea nodules taken and trying to recover cobalt from there also. I think I should stop over here. Chairman was standing and trying to control. Thank you very much for your kind attention.
Friends, time allotted to Tiwari Saab is not enough for him to go through every aspect of nuclear energy, material production, and all sort of troubles we have. But still, he will be able to answer some questions, few questions, if you can raise those. Yeah, please.
What is the fuel we are going to use for SMR?
See, SMR, we have two approach. What is called BSMR, the Bharat SMR. And
Is it same as PHWR or 200?
yeah, see what we are trying to do is, see one word is modular. That we are taking in BRC. Modular means what? That you make all the component in a factory and just go and assemble there. That can be done. Right now we go with the custom made kind of thing. Design is not standardized and we see by the demand process and make it. Now that is being done. For 200 megawatt we have done, given the proposal. Second is that in all these small reactors, Government of India has a policy that NTPC, all the old plants will not be given any renewed license. We need to convert all NTPC plant into the nuclear reactor, that is BSR. So in that what happened, 200 megawatt, we are making a special containment so that the exclusion zone can reduce to half kilometer, which is the typical size of the NTPC at this point. This and 4 companies, Tata, Reliance, Adani, and one L&T. Jindal. So these people have already started working with us. NTPC is already working with us. So this first reactor was expected to come by 29 or 30 somewhere.
So if there are no more questions, let us thank Tiwari Saab for one question.
Sir, compared to thermal power plants and all, is it more economically feasible for to implement nuclear power plants?
No, actually I tell you, the problem is low efficiency plants, they are easier because you are burning water, finally you are boiling water. So then it appears, but the kind of total environmental damage, if you want to compensate, then it becomes very, very costly. So that is where nuclear energy had 2 problems. One, that initial cost was very, very high. See, till 1990, India was not in a position to finance too many reactors. It's not that we were inefficient. Now every year we are putting 700 megawatt reactor. Even if you check in the Google or news and this thing, even yesterday RAP 7 was joined to the grid. Every 1 year we are making 700 megawatt reactor, every year 1. And we have to now make it 2. That is the government compulsion. That is where when they are talking about 100 gigawatt and all, at least you have to stake from somewhere. This is not the problem. The problem with the coal now is we have already consumed our best quality coal. Like Jharia mines in Jharkhand is the only small source remaining. Rest we have consumed. Now we are importing coal from the Australia and other countries. If you add that running cost, 10-year running cost with the cost, then you find nuclear is actually outsmarting the thermal plants.
Thank you, sir.
Thank you. After the Malhotra's lecture, you can ask him. That is also possible. Just wait for his lecture. Afterwards, you can answer. Thank you. Next talk is by Dr. Malhotra. He will talk about zero emission aim.
Just to hand over a memento.
Hi, please.
Thank you, sir. We had an inspiring session. Now it's time to express our gratitude. We would like to present a memento and a book title on the wheels of education serving USA in India, written by Professor Sree Krishna, a renowned scientist. For this, I invite Dr. S.V.G. Menon, sir, to give the present.
So now we are moving to the second session. Second session will be handled by Sapnesh Kumar Malhotra. Dr. Sapnesh Kumar Malhotra superannuated from the Department of Atomic Energy in 2015 after serving for about 4 decades. He was immediately awarded Raja Ramanna Fellowship and was appointed as Secretary, Atomic Energy Education Society by Department of Atomic Energy. He laid down this office on completion of his term in 2019. After post-graduation in chemistry from Agra University in 1976, he joined BAR. For more than 2 decades, he was engaged in research and development on heavy water and important nuclear material for the Indian nuclear power program. His area of interest include hydrogen isotope separation, fractional and cryogenic distillation, analytical techniques, etc. Based on work carried out by 2 iteration plants are operating in BAR. With immense pleasure, I request S.K. Malhotra sir for his talk.
Thank you. Now friends, without wasting any time, because I have to, after finishing the lecture, I have to catch the flight. If you look at your abstract book, you will find that the topic given by me for my talk was somewhat similar to what previous 2 speakers have spoken. And then my great friend, Dr. Surendra Nathan, who is president of the Atomic Energy Retirees Association, he made a special appeal to me that you give your popular talk about the public perceptions about atomic energy, for which I have not brought any slides. So I am going to speak extempore to you. I will try to finish in 30 to 40 minutes, and I will try to reply to most of your questions. So I think let me start my lecture with a question only. This young man wanted to ask a question. What was your question? Come here, come here. Don't waste time. Come here. Ask your question.
My question was the working of tokamaks and stellarators, how their methods differ and how fusion is achieved in both of the methods. Tokamaks and stellarators. That was my question. How they achieve fusion. How are their methods different?
Yeah, I will. So see, whenever you have to carry out fusion, your operating temperature is about 10 to the power of 6 to 10 to the power of 7 degree. Okay? And at such a high temperature, there is no need to tell whether it is Celsius or absolute temperature. Everything becomes almost same because the temperature is so high. So it is 10 to the power of 7 degree temperature. At that temperature, none of the material you will use can exist in physical form. Everything will turn into plasma. Okay? So the question is, when you are doing this and ultimately you want to take out the heat. So this plasma, where will you contain? How will you contain? See, you have to use a magnetic field. So that tokamak is a magnetic device in a magnetic vessel. In a magnetic field, you store the plasma, and there you will carry out the fusion reaction. Okay, so that is all about it. And in India, we have two such systems operating at Ahmedabad, Gandhinagar actually, the capital of Gujarat. There we have two systems. One is called Aditya, and another is known as SST-1, Solid State Tokamak 1. Both are operating, and as was told to you in the previous lecture, we are also participating in the ITER. India is one, and India is not making any cash contribution. Our contribution is only in the kind. So we are making systems and supplying to them. There is a separate package. It is called ITER India package, under which Department of Atomic Energy, its units, and even private industry like L&T, I can name one, they are making the system a contribution, and India, I think, is going to make a great contribution. That answers your question. So anyway, friends, since morning you have heard that India has committed for a net zero emission by the year 2070. That means your carbon footprints will become zero. What is carbon footprint? That means whatever carbon dioxide you are producing, you are either storing it or you are removing it from the scene. So net carbon dioxide which will go to the atmosphere will be zero. That is what is meant by net zero. Now India has promised that by 2070 we will achieve net zero. Now how to achieve it, I think previous speakers also told you, but in nutshell I will tell you, for this you require to do two things. Number one is electrification, major electrification of our economy. Many places where, for example, you want to produce heat. So you go to any factory, they require process heat. What do they do? In the olden times, there used to be a boiler house in every factory. Boiler house will burn coal, produce heat, and water will be boiled, and that steam will be taken around in the factory, and wherever you need process heat, this steam will provide I think any old textile mills, this used to be the scenario. Okay, then next they started burning the petrochemicals, means furnace oil. You must have heard that furnace oil is used, and various kinds of fuels are burnt, and again water is boiled. So, but now there is a thinking that we have to get rid of all these fossil fuels. Nothing is to be burned, neither coal nor petrochemicals. What we are going to do is that you produce the heat electrically or directly by nuclear power. So wherever in a factory, if you need a small amount of heat, I mean if it is, the amount is not very large, then you use electrical heating systems and produce the heat. But if it is a very large establishment, you have a nuclear power plant there, an SMR there, which will produce the heat. So that is why I think it was mentioned by the previous speaker, BRC is developing what is known as high temperature reactor. So high temperature reactor will provide this heat in addition to providing nuclear power, it will also provide for hydrogen. So one thing is that in the industry you have to identify wherever currently we are using fossil fuel, etc., we have to replace it by electricity. So major electrification of the economy. And second, what we have to do is that places where this is not possible, you have to change some of the chemical reactions. I will give you a very popular example. I think all of you must be knowing about blast furnace, which is for converting the iron ore into iron. Okay, how it is converted? See, iron ore is basically the oxides of, oxygen is there. So basically you require a reducing agent to convert the oxide or silicate, whatever is the iron ore or sulfide, you want to convert it into iron. So that means you want to reduce it. So what is the reducing agent used in blast furnaces for last so many centuries that iron, the mankind is producing? It is the coal which is used. So coal there is not used as a fuel. It is used as a reducing agent. So what you do, iron ore plus coal, and you burn that coal, so heat is produced at that high temperature. The oxygen of the iron ore is taken up by the carbon, so it gets converted into carbon dioxide. It is released to the atmosphere and you get the iron ore. So now what we want to do? The problem is that carbon dioxide is being produced. So, but you want to stop production of carbon dioxide. So what you do? You use hydrogen as a reducing agent. Instead of using coal, you produce hydrogen by some means in which carbon dioxide is not produced. That hydrogen you use as a reducing agent, it will do the same work which coal was doing. So hydrogen will take up the oxygen from the iron ore and will get converted into water. H2 plus O will give you water. So no carbon dioxide will be produced. So this is only one example. If you scan the whole chemical industry, you will find so many examples wherever, cement industry, etc., wherever you are using reducing agents, you replace coal by things like hydrogen. So this is one thing. But still the challenge remains very high. If we do all this and for our economy to grow strong, our energy demand, I am not saying electricity demand, our energy demand in next 30 to 40 years is going to increase fourfold. Okay, but if we are shifting towards electricity for achieving net zero emission, our electricity demand is going to increase by 12 to 15 times. Whatever, today we are generating about less than 2,000 terawatt hours or billion units. I think that is better. So we are producing less than 2,000 billion units of electricity per year in India. From there we will have to go to 28,000 billion units of electricity per year. So which is a very, very high demand. There are some people who for some reason do not like nuclear power. They say renewable will do the job. But the problem is I will not go whether renewable should be done or not done. The question is, in my kitchen I have resources. I have to go by that how much rice I am having. I can cook only that much rice. I don't have any extra rice to cook. So out of this 28,000 terawatt hours, only 8,000 terawatt hours can be produced in India by using renewable fuels. Solar, wind, everything put together, maximum 8,000 terawatt hours per year will come from renewable power. So remaining 20,000, either you burn coal or you go for nuclear. So in fact, that is why I have given the title of my original lecture, which I was to deliver, that it is inevitable option. It is, you cannot achieve net zero emission without indulging in nuclear power, whether somebody likes it or not. It is not possible. Now, why are people afraid of nuclear power? Normally, if I had time, I will ask questions to the students. But I think I will myself become a student and I will pose the questions and try to give you the answers. So first question is, what comes to mind is safety. People say, oh, nuclear reactors are not safe. So in fact, I would have loved to ask you a question, whether more number of accidents have happened in nuclear power plant, let us say in last 30 years. In last 30 years, whether more nuclear power accidents have occurred or accidents associated with coal mining and usage, they are more. I will give the reply. There are data available. I am not speaking out of imagination. There are statistical data available. In last 30 years, there have been more than 2,000 accidents in industry associated with coal mining or usage. In hydroelectric power, I am not speaking against hydroelectric power, but in 1976, one single accident in China where the dam burst, in 3 hours time, 30,000 people died. 30,000 people died in 3 hours. And in next 3 months, because of the epidemic diseases, another 1 lakh people died. Okay? Now, how many nuclear accidents have happened? I think I will answer the question to save time. As per the definition of accidents, there are only 3 major accidents which have happened. In fact, some people say only one has happened, Chernobyl, because I will name the 3 accidents. 3 Miles Island accident, which happened in 1979, which as per the definition of certain people, there is a Paul Scherrer Institute in Switzerland who are known as the account keepers of accidents in the whole world. So as per them, any incidents can be declared as an accident only if minimum 5 people die. If less than 5 people die in a bad incident, it cannot be listed as an accident. So if you go by that definition, there has been only one accident, Chernobyl, because in the 3 Miles Island accident, nobody died because something happened to the reactor, the core got damaged, it melted, but it remained inside the reactor building. So nothing came out, no radioactivity was released, no operator was harmed, no general public was harmed. Nobody died. So they refused to list as an accident. It's a bad incident, abnormal incidents. Similarly, Fukushima, nobody died. You know, people will say, sometimes in Japan, because of this accident, the flyovers falling down, the trains going into the sea, the ship coming to the land, because of that around 18,000 people died. None died in the nuclear power plant, none. In fact, one dead body was found inside the reactor building, which was found that it came by floating from the seaside. That person did not belong to nuclear industry. So what I am trying to say is that normally, you know, there are people who are afraid to travel by air. They refuse to travel by air. 24 hours, I'll go by train. I'll not go by one hour plane because plane falls down. Again, you look into the statistics. I think year-wise the statistics, you can Google it. Nowadays, I don't have to say anything. You can Google it. Find out in 2024 how many people died because of heat button. Here is the button. You can Google and find out in 2024 how many people died in air accident, how many died in rail accident, how many died in road accident, how many died while walking. You will find that maximum number of people died while walking. So if you want to go by number of deaths, walking is the most, walking on the roads is the most unsafe method of traveling. And air is the safest method because you will find from the statistics, okay, when an see what happens when a pedestrian dies, a single pedestrian dies, let us say in Cochin, another dies in Lucknow, one fellow. So every day, actually hundreds of people may be dying in road accidents, but that is not one incident. While a plane, when it falls down, 300 people die in one go. So it appears big to you, but otherwise, actually traveling by air is one of the safest methods of traveling. Similarly, if you go by statistics, if you go logically, nuclear power is one of the safest methods of producing electricity. So that is about the safety. Second thing is people talk about the waste. That highly radioactive waste is generated from the nuclear power plant. So what about it? So my question is actually normally, again I ask this question to the students. Please tell me, this question I will really ask. There are two living beings, lion and mosquito. Those who feel lion is more dangerous, raise your hands. Out of the two, lion and mosquito, lion is more dangerous, please raise your hands. So nobody feels lion is dangerous? Please participate, save time. Acha, those who feel mosquito is more dangerous than lion, they raise their hands. Now, for example, now you raised your hand. I don't want any fence sitters. You have to raise hand either for either of them. Yes, you. Mosquito or lion, which is more dangerous? Huh? Mosquito. What about you? Mosquito. 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 Anybody wants to vote for lion? Anybody wants to vote for lion? Okay, you want to vote for lion. So we will do one thing. You come in the flight with me. Tomorrow I am going to another state. There is a lion safari there. There are forests there. I will leave you in the jungle. And night, 12 o'clock, you tell me whether lion is more dangerous or mosquito is more dangerous. See, sitting here, everybody is telling mosquito is dangerous. Now, sitting here, when you are sitting here, lion is more dangerous or mosquito? Mosquito. When you are sleeping in your house, lion is more dangerous or mosquito? So when does lion become more dangerous? When you are in the jungle. Okay? But if I ensure you that the lion from the jungle will not come near your house or near your college, then who is more dangerous? Mosquito becomes more dangerous. So many times what happens? Isolation. See, something may be very hazardous. Your mother cooks in your house. She burns a fire every day. Okay? She knows how to operate safely. Okay? So even if a hot vessel she wants to lift, in the old times they used to use a piece of cloth, some old towel or something. Nowadays gloves are available. So they use them. So they know that if directly they touch a hot pot, their hands are going to burn. Okay? And if they don't follow the procedure, then heat will become dangerous. So similarly, lion is at any time, if at 1 meter distance from you, there is one lion and one mosquito, lion is more dangerous. So if they are at the same distance at the same time, lion is more dangerous. But in practical life, find out from the hospital, local hospital, how many patients of lion bite came to their hospital and how many patients with mosquito bite came to that hospital. You will get your reply. Okay? So we have to bother about mosquito. See, Government of India, you look at Government of India, it is spending money to save the lions and kill the mosquitoes. Okay? They supply, I think, for many decades when I was a child, they used to supply free DDT powder to the houses that you sprinkle it so that the mosquitoes will die. Okay? Though, actually, lion is more dangerous. But as lion is isolated from us, under normal circumstances, lion is isolated from us, so mosquito becomes more dangerous. So similarly, my dear friends, I want to tell you, radioactive waste is like the lion. It is more dangerous as compared to carbon dioxide. Okay? Carbon dioxide is an innocent molecule. Actually, we are living because of the carbon dioxide molecule. Because there is carbon dioxide in the atmosphere, so with the help of sunlight, food is being prepared by nature. Food is not prepared by your mother in the kitchen. It is prepared by the mother nature in the trees and plants. Okay? And whether you are vegetarian or non-vegetarian, you are eating the products of photosynthesis. Okay? Even the animals we eat, they are eating some green vegetables which are being prepared by photosynthesis. So we all are dependent on photosynthesis. Okay? So carbon dioxide is essential for life. But our problem has become that nature was producing sufficient carbon dioxide, the world was going on peacefully, and then we discovered fire. I think many thousands of years back, fire was discovered. So they started burning firewood, coal, etc. But they were burning in limited quantities. So they were, in fact, they were not disturbing the natural carbon cycle. Okay? But now, after the 17th, 18th century, what has happened? The nature which prepared the coal in millions of years, we have practically burnt it off in 300 years. I think morning also you heard that coal is practically, I think it is getting extinguished from the world. So nature took millions of years to prepare that coal, but we have consumed it in 300 years. And consuming is not that big a crime. By consuming that coal, we have produced every 12 gram, please note this fact which you know. I am only activating you. Every time you burn 12 grams of carbon, 44 grams of carbon dioxide is produced. Okay? Please remember that simple chemical equation. C plus O2 giving you CO2, carbon 12 and oxygen is 16. Okay? So that tells you that 12 gram carbon gives rise to 44 grams of carbon dioxide, and that has become our problem like the mosquitoes. The population of mosquitoes has increased like anything as compared to the lions. So we are dying of malaria and dengue. Similarly, carbon dioxide, though essential for our living, but its amount in atmosphere has increased so much that the temperature of Earth is increasing, and that I think rest you know climate change etc. is happening, and that is why UN is having, UN has given 17 sustainable development goals. They are known as SDG 1, 2, 3 to SDG 17. Go and Google SDG, just ask the question, what is SDG 13? You will say Climate Action Plan. SDG 13, the Sustainable Development Goal of UN, number 13, is about action, climate action plan. And what comes under climate action? That reduce the generation of carbon dioxide. Nowhere it is written that reduce nuclear power. It is written reduce carbon dioxide. And the type of lifestyle we are enjoying, the type of industrial revolutions we have done, we cannot do without electricity. And if you are being told that you cannot generate carbon dioxide, nuclear is the only option. So waste management, whenever you look at a nuclear waste, yes, it is more dangerous than carbon dioxide. But then the thing is, thousands of engineers in Department of Atomic Energy, one is sitting here, I remember, Mr. K.N.S. Nair, please raise your hand. Throughout his life, he worked on nuclear waste management. He was involved in that program. He is my batchmate. And throughout his career, he has worked only on one problem, that how to isolate nuclear waste from the public domain. So it should not come to the public domain. Unfortunately, what is our problem? Our daily life, we are ourselves committing so many crimes that we think everybody must be a criminal like us. What crimes we are committing? You go to a roadside shop and there he gives you dosa on a banana leaf. And in North, I go to eat samosa, he gives me on another dry leaf. He gives me, we eat it and we litter it around. So we feel that wherever waste is generated, it will come to the public domain. The right way would have been that banana leaf on which you have eaten the dosa, in a proper dustbin you should put it. Next day somebody should empty that dustbin, take it away and reprocess that. So that some useful products will come out of that, make manure out of that. But nothing happens. Outside the dosa shop, you will find last 15 days banana leaves, they will be lying there. So that is why we think that in nuclear power plant also same thing must be happening. I think in the previous lecture you were told that nuclear waste actually is not a liability to us. It is something very useful. Two examples were given by my friend Tiwari, that ruthenium is extracted from the spent fuel, from the nuclear waste. Ruthenium is extracted and it is used for cancer treatment. Similarly, cesium-137 is recovered from nuclear waste. And it is used in actually nowadays people are working on the fact that all cobalt-60 will be replaced by cesium-137 wherever it is possible. So in fact, nuclear waste is a very important resource for us. Ultimately, whatever we think we cannot use today, we don't throw it. There is a complete technology on which Nair and his colleagues, they have worked throughout their life. The nuclear waste is converted into glass. Now you will ask the question, why glass? Why not steel? But why glass is used is, reason being that glass is a very greedy material. If we talk in scientists' language, we will say the leaching coefficient of glass against water is very, very low. What does it mean? It means glass is a greedy material. If glass, this water I just drank from the glass, now if you look at the composition of glass, it is a very dangerous composition. There are certain elements in that which I cannot eat. But I am drinking water kept on that glass. Why? Because I know glass is a very greedy material. It will not give even one atom to that water. So that atom of the glass will not go into my tummy. So with that confidence, not only me, all of you, we are drinking water from the glass. Although knowing that glass is I can't eat glass, but I can take water contained in the glass. So similarly, we have, for this property of glass, that glass being a greedy material, we convert radioactive waste into glass, so that even if by mistake it comes into contact with groundwater, none of, even a single atom, radioactive atom will be passed on to water. It will remain in the glass only. But that doesn't mean that we throw it in the river or in the sea. After making glass, we store it in a double-walled stainless steel vessel and then keep it in lead flask, and then in an engineered manner, I never use the word bury. We keep it in some deep geological places, about 2 kilometers deep. We intend to keep it there so that in future if we need it back, some technology will develop that we can use some of it. We can easily take it out. So I think there is no need to be worried from nuclear waste as long as our engineers are working, as long as they are working to ensure that the nuclear waste will be isolated from the public domain. Carbon dioxide is more dangerous. And here, standing here in this college, I am making a declaration. Anytime if life on this earth becomes extinct, take it from me, it will not happen due to radioactive waste, it will not happen due to nuclear power, it might happen because of increased concentration of carbon dioxide. If we keep opposing nuclear power, if we keep burning coal, one day will come that life will become extinct. And that day, I think while all of us, while dying, we will feel, I think nuclear was better. So anyway, third question which comes to the minds of the people is that about the cost. Some people feel, I think a question was also asked, that cost. So he gave a beautiful answer that the environmental harm, see today what is there, you in a factory or in your vehicle, from your vehicle lot of smoke is going out, there is nobody to check. Though RTO there are rules, but nobody bothers. From the silencer, so much of smoke is coming out, but nobody is bothered. But if we start charging for the environmental damage done by every industry, every individual, suppose some such rule comes in future, then coal-based power will become the costliest power. It will become the costlier. These are called as overhead charges, okay? So, as long as you are not being charged for spoiling the environment, okay, coal and nuclear may be competitive. So this is one thing. Another thing is that don't think that nuclear power is a very costly power. Just to give you an example, you can Google what is per unit cost of electricity produced from Tarapur Atomic Power Plant 1 and 2. It is one of the lowest in India. Even today, less than 1 rupee 10 paisa per unit. We are producing, I don't know in Kerala per unit electricity is how much? Maybe more than 6-7 rupees? 8 rupees. 8 rupees. And at Tarapur 1 and 2 in Maharashtra, we are generating electricity at less than 1 rupee 10 paisa per unit, and the maximum, the costliest electricity from a nuclear power plant is 4 rupees 68 paisa per unit, which is in one of our latest plants in Gujarat, Kakrapar unit 3 and 4, there the cost per unit of electricity, that they say the government decides the tariff. So that tariff has been decided at 4 rupees 68 paise. That means we will sell electricity to the grid, power grid of India at 4 rupees 68 paisa per unit. So we are I am not telling we are cheapest, but we are very competitive. So there is no need to be worried that nuclear power is very costly. Another question that comes to my mind is that, okay, some people say that, okay, accident is not happening. But a nuclear power plant continuously must be releasing some radioactivity and some radiation into the atmosphere. So people feel that the people living near a nuclear power plant, they will be suffering from cancer, they will be dying because of excess dose of radiation. But let me tell you, morning somebody gave you an example. I think Sir gave an example of X-ray. You gave example of X-ray. Whenever you go to a doctor, 15 days you are coughing continuously. All medicines, cough mixtures are not working, then the doctor finally says, go and get a chest X-ray done. If some of you recall, the protocol during the COVID period in the hospitals became that even if you are going for a fracture to the hospital and you have to be admitted, your X-ray will be taken to find out whether you are affected by COVID or not. You will be admitted only if your lungs are free of any damage by COVID. Otherwise you will not be admitted in that hospital. They will say go to some COVID place. Your lungs are damaged because of COVID. So whenever an X-ray is taken of chest, the dose you receive is, I will not go into the units, just look at the numbers. 50 microsievert is the radiation dose received in one X-ray. And if you live next to nuclear powers, if this is the nuclear power station, just outside the window you build your house, then in 1 year you will get 50 microsievert dose. So in 1 second, one X-ray, what dose you will get in 1 year if you live next to a nuclear power station. So this myth that nuclear power is continuously emitting radiation and radioactivity into the atmosphere, we have full-time career. Some friends are sitting here who have throughout their life, they have worked on health physics. Some of them will be speaking to you. So they are known as health physicists. Their job is only to find out that in the vicinity of the nuclear power station or any nuclear facility, as a matter of fact, what was the radiation before that facility came, and after it has become operational, whether the radiation level is increasing. Everywhere, at every nuclear facility, we have a network of these health physicists. We have a network of radiation measurement, ERMON it is known as, IERMON. We keep on monitoring radiation, and let me tell you, some of the nuclear power stations in the vicinity of them, the radiation levels are much lower than some places within our country. For example, your own state, Kerala, if you go to the eastern coast of Kerala, the sand is full of, it is containing thorium, and because of that it is radioactive, and the average natural background radiation on the coasts of Kerala is 30 to 70 times higher than the average natural background radiation. If you go to Brazil, there it is 400 times higher. Brazil's similar beach is there, and there the radiation levels are 400 times the natural background area. So I think we are living, and we have Department of Atomic Energy has conducted studies in this radioactive belt of Kerala. We sponsored that research, and registries were established, 2 types of registries, that whether cancer occurrence is more in that region, just concluding, in that coastal region, whether more people are getting cancer per 1,000 people, we found they are at the same national average. Similarly, it was also studied that the newborn children, whether more number of newborn children are having genetic diseases on the beaches of Kerala as compared to the rest of the country, there also it was found that no, there is no increased number. So even in a place where radiation background is 35 to 70 times higher, there is no effect, and definitely around a nuclear power station the radiation levels are low. I think chairman is indicating that my time is over, and even I feel that I must rush towards the airport. So I have tried to answer some of the questions which might be in your mind about nuclear power. Anyway, my colleagues are here. They are better experts than me. Kindly interact with them. Only problem I am finding with the students is I have not seen even a single student, maybe except one from there, open their mouth. Please be interactive. The organizers have spent lakhs of rupees in arranging this program. For example, they have sponsored my ticket from Bombay to here, and today I am going from here to Bhubaneswar. All ticket is paid by the organizers. Okay? So make good use of that money. It is good money, so make good use of that. Please ask questions. Don't ask me because I am in a rush. You can ask others the questions. Thank you very much. God bless all of you.
Friends, let us thank Malhotra for an excellent speech, and you can ask 1 or 2 questions if you have. Of course, he can answer those questions during lunch also. Then you can ask him in a comfortable way. But before we conclude, I would like to give you that momentum. So this session is over. We will get back after lunch as quickly as possible.
Sir, please. Now for presenting mementos for Dr. S.V.G. Menon and Dr. Nishanti, I would like to invite Dr. K.K. Surendranathan, sir. Sir, please.
My lecture is going to come after lunch.
For chairing the session.
Let me have the pride in welcoming Dr. K. Bhaskaran Pillai, sir, for receiving the present. For honoring him, let me invite Dr. Vijay P.S. Sir, please. Thank you once again to our esteemed guests, resource person and fellow enthusiasts. We will now take a short break for lunch. Please join us back here at 2:50 p.m. for the commencement of the technical sessions. We will now adjourn for lunch. Lunch will be served for students at 51 m. Token for lunch is provided with your registration kit. We look forward to seeing you all back here shortly. Thank you. 51M is on the ground floor.
Low, cheek, cheek, cheek. Low, cheek, cheek, cheek. Low, cheek, cheek. Low, cheek, cheek. Low.
Mic ഊതിയോടെ മൈക്ക്
ആയിക്കോട്ടെ.
Hello. Welcome back. I hope you all enjoyed the lunch. We will now proceed to session 2, and we have an exciting lineup of speakers for this session. Dr. S.V.G. Menon, former distinguished scientist and group director, retired BARC. Dr. M.M. Mustafa, professor, Department of Physics, Calicut University, Kozhikode. Dr. Erain Kumar, assistant professor, Department of Physics, KUSAT, Kochi. And S.V.G. Menon sir is on the topic nuclear fusion, current research and prospects, followed by Dr. M.M. Mustafa on the topic nuclear reactors towards energy with zero waste, and Dr. Erain Kumar, artificial intelligence in nuclear physics. And this session is chaired by Dr. R. Tiwari, distinguished scientist and director, materials group BARC, and this session is co-chaired by Dr. Rajesh Kayar, HOD physics, SKC, Guruvayur. Over to Tiwari sir.
Yeah, good afternoon. May I invite Dr. Menon? He has already been introduced. So to save the time, so I will straight away probably take over the stage. Thank you. Please.
Yeah. Oh, it is audible now. Oh, introduction. You want to read? Okay. It was already read this morning. Morning it was done. It will be repetition. You only. Morning it was done. Introducing me was already done in the morning, so I requested him don't repeat it because sometimes it is boring to hear about what others are. Today for me it is a tutorial lecture. I am here basically because of my old friend T.R.G. Kuti, because he contacted me some time back last month, asked me to come here for this conference. I have some throat problem, but I suppose I will be able to deliver this talk. It is basically for students, and I suppose you can come forward and listen more carefully about this talk. So, what I am going to talk about today is very basic physics. What is fusion, number one. What is magnetic confinement, and what is laser-induced fusion. And there are two schemes in that. What is called direct drive, laser-induced fusion, as well as indirect drive. There are two schemes. And finally, if you ask some questions, I will be able to answer. Fusion power is a source of energy in the universe, that all of us know. All the systems in the universe are powered by fusion reaction. And of course, fusion reaction is taking place because of gravity keeping the objects like stars or similar objects. The sun produces about 3.8 into 10 power of 20 megawatt of power. That is too huge to even imagine, but it produces that much amount of power from the sun. But out of that, what is coming to Earth is only 4.4 into 10 power 10 megawatt. That is because Earth is very small, and whatever comes within this solid angle also will not reach Earth. Some photons will go away. So only those photons which are directed directly to Earth only will reach, and we get about 4.4 into 10 to the power of 10 megawatt of power. The world requirement of electricity in 2022 was only 7.4 into 10 to the power of 6 megawatt only. So we are getting at least 4 orders of magnitude more power from sun to earth. And always there is a puzzle, at least for physics people, that what is the problem when we are getting so much of energy from the sun? Of course, as Dr. Tiwari pointed out in the morning, and Malhotra also amplified, there are technological problems to realize this. Otherwise, we are getting ample amount of energy from the sun, and all species in the universe or in the planet Earth are satisfied with this power. There is only one species, that is Homo sapiens, that is ourselves, are looking for different form of energy or different form of power. It's a surprise that why only we are not satisfied with this naturally available power. So, as was explained, there are technological difficulties to harness this 10 power 10 megawatt of solar power which is falling on Earth. Otherwise, we have plenty of power. We don't have to burn coal, we don't have to do hydroelectric, we don't have to do any form of energy source, we don't have to look at. But there are problems. That's what I am going to talk to you. Fission and fusion are two types of nuclear reactions from which we can extract energy. In fusion, fast particles like deuterium and tritium, mass number is 2 for deuterium, for tritium it is 3. They join together and a neutron is produced, and what will be left will be a nucleus of alpha particle, nucleus called alpha. In the fission process, the heavy nucleus like uranium-235 is bombarded with a neutron and it splits into 2 fission fragments and produces 2 fission fragments. One possibility is rubidium, another possibility is associated with rubidium you will get tritium. And additionally, roughly about 3 neutrons are also produced, and these neutrons can be used to cause further fission, and we can imagine a chain reaction which is taking place. If the chain reaction is contained, then you will have reactors where power is produced at a constant rate. If chain reaction is not contained, we have the bomb. So what possibilities are there? And the beauty is that in a matter of 5 years after the discovery of fission, the reactor was made. And about fusion, I will come and explain to you. Even after 80 years, it has not been possible to make a fusion reactor which will generate power at a decent rate, which is useful for us. Nuclear reactions produce about a million times more energy compared to chemical reactions. Chemical reactions take place at the level of electron volt. Physics people will know. And here it will take place at the level of million electrons. So that is why the reactors based on nuclear process are small, because you get more energy from one reaction. So you don't have to have too many reactions at time. Nuclear fission, of course, you should also see about nuclear fission, because Department of Atomic Energy is primarily interested in nuclear fission, even though there are laboratories and centers working on nuclear fusion also. A neutron bombards a nucleus, a compound nucleus is formed. The compound nucleus is not stable because it is formed in an unstable state. It splits into two fission fragments, gamma radiation and some neutron, additional neutron. And in addition, in this process, you get 200 MeV of energy from one reaction. Bottom are shown two possible reactions U-35 plus a neutron giving krypton and barium and 3 neutrons and energy 200 MeV. Another possibility is you get molybdenum and lanthanum and 2 neutrons because the reactions are statistical. Sometimes you get 3, sometimes you get 2, and sometimes you get some isotopes as fragments, sometimes something else. So it is a statistical process. Nuclear fusion is, as I explained already, you start with deuterium and tritium at the bottom. Deuterium has got 1 neutron and a proton. Tritium has got is an isotope of hydrogen, 1 proton and 2 neutrons. These can be combined together. You can fire one against the other and produce something like a compound nucleus which will split. When it splits, it produces helium plus a neutron. This is the basic process. A DT reaction produces 3.5 MeV as alpha particle energy and 14.1 MeV as neutron energy. The fusion of 50-50 mixture of DMT produce about 80.4 into 10 to the power of 12 calories per kilogram. 10 to the power of 12 calories has got a unit, it is called kiloton. People who deal with this subject are more familiar with that unit of energy, kiloton. Kiloton is 10 to the power of 12 calories, is 1 kiloton. So 80.4 kilotons are possible by burning 1 kg of thorium mix. Whereas if you burn 1 kg of whereas if you take 1 kg of uranium to fission, you will get 17.6 kiloton of energy. So that way, the reason is very simple, because deuterium and tritium are very low mass. So per kg, when I convert, the number of pairs which are available for reaction will be actually more, and you get more energy per kilogram. Pardon? But the problem is, deuterium and tritium nucleus have got charges. As I told you, each are isotopes of hydrogen, so there is a proton in each one of them. So when you try to bring them closer, there is electrostatic repulsion. So you have to overcome. Unless that is overcome, they will not come and fuse. It is not possible to keep one deuterium nucleus and one tritium nucleus close by, and they will react automatically. That is not possible. Because the Coulomb force have to be overcome, and you have to fire one against the other. That is the requirement. And there lies the entire problem. The one entity of energy, if you want to keep it in mind, it is 10 power minus 13 joules conversion. The DT fusion is used in ITR, International Thermonuclear Experimental Reactor. I will come to that later. So the modern point is you have to overcome the Coulomb force to make two nuclear fuse. So thermonuclear fusion temperature is raised for the mixture so that reactions can take place. Research on thermonuclear reactors started way back in the 1940s. As soon as fusion was discovered, actually fusion was known even before that. 1930 itself, Bethe had proposed the reactions which are responsible for energy from the sun. So people knew it, knew about it. But going into details of the reaction mechanism and the way to harness that energy, people started working way back in the 1940s. So almost 80 years have passed, and we are trying even today, people are trying even today to have a workable system where energy can be drawn. To fuse deuterium and tritium, energy is needed to overcome electrostatic repulsion. One way is to heat the material to high temperature. You have to heat it to 50 to 100 million degrees. Then only useful reaction will take place. 15 million degrees is roughly 5 keV of temperature. If you convert the degree to energy, it will come to about 5 keV. So 5 to 10 keV, you have to raise the temperature of the mixture. Generally, fusion reaction will take. But then what happens? The material becomes what is called a plasma. So plasma at a temperature of millions of degrees will not stay as it will run away. All systems, when you are keeping at some temperature, they will run away simply because of the temperature is nothing but the kinetic energy of the atom, and if they have kinetic energy, they will run away. So two schemes have been people have been working to contain the plasma and generate energy. One is magnetic confinement, where the plasma is very low dense, like not even air density, like 10 power 14, 10 power 15 number of particles per second. But you have to confine that for a longer time. So long confinement time and low density is the characteristic of magnetic confinement. Whereas initial confinement, you make the density of the mixture 1,000 times the solid density. I will tell you exactly how it is done. And because you can increase the density, if you can increase the density 1,000 times, then the confinement time can be brought down so that useful number of reactions take. So initial confinement, the mixture is raised to 1,000 times the normal density. So the confinement times are only nanoseconds. And the initial confinement is very closely associated with weapon technology. So most of the things about inertial confinement are classified. We will not know what goes on in the laboratory, particularly US and France or UK, or they will not, simply will not. So we have to generate everything ourselves, and DRC is one of the jobs is developing the thing without depending upon outside because outside people are not going to. Stars like the sun confine material because of gravity. No magnetic field is required to confine it. Magnetic field is produced because of motion of the charged particle. But it is not necessary for the sun to confine. Only gravity is enough to confine the plasma and produce. You know that the surface of the sun, the temperature is only about 6,500 to 7,000 degrees. but inside the sun, right at the center, it is 1.5 million degrees. So that is why the fusion reactions take place there, and the photons diffuse. It takes years and years for a photon produced today to diffuse, because sun is so huge. So, and that is what we receive. It is good to know what are the various states of matter as you trace them. You start with minus 273 degree, which is absolute zero, which is not attainable, as it is the lowest temperature which can be known. Then if you go to 273 K, that is room temperature, you have got normal solids. Normal solids exist at temperature range. You further raise temperature to boiling of water, 100 degrees, or melting of metal is 2000 degrees. So, and surface of the sun, which is 6,000 or so it is the region of liquids, gases, and arc like plasma. So plasma begins to come after about 10,000 degrees. So the electrons are ionized from the atom. So you will have a mixture of ions as well as electrons. That's what plasma is. Ionized gas is famous plasma. Center of the sun, as I told you, about 15 million degrees. I said 1.5 keV, so it is 15. Fusion on Earth, as I told you, we require still more. Not even what is happening at the center of the sun. We want 50 million to 100 million. That is 5 keV to 10 keV of energy. Then only workable, useful energy can be extracted. Magnetic fusion is one of the international efforts goes on to harness energy via magnetic fusion is tokamak, that is the center of the thing you can see. It is a torus shaped object, and magnetic fields are produced by coils going around the torus as well as along the center of the torus. And the particles are supposed to move around the center of the torus, and occasionally they will make collide and fusion reaction is possible. This is the idea of magnetic. The plasma moves along the center of the torus. This is only a sketch. The actual size of this, if you see, it will be as big as this, or maybe even bigger. So it's difficult to maintain such a large system with homogeneous magnetic fields, and collisions are unavoidable, because unless the plasma ions collide, we will not have these things produce instability, and it will not be confined for the required time. Before that, the plasma will go and hit the chamber surface and the reaction. The low confinement time is the problem because of inhomogeneities of the magnetic fields, as well as the collision between the atoms destabilize the plasma. Please. No. It is because even though the atoms have got high lot of energy, there is no melting of the chamber. What will happen is the chamber will be spoiled because of bombardment by these atoms. It is not temperature which is going to damage the thing. It is the sputtering of the particles going in. It will spoil the chain. So there is what is called the Lawson's criteria for useful fusion reaction to take place, so that we can expect it is number of particles per cc, that is n. You can count both of them during my times the confinement time. Confinement time is told this should be greater than 1.5 times into 10 to the power of 14 seconds per cc. N has got dimension of per cc and tau has got dimension of second. So the right hand side has got dimension second per cc. So this should be more than 10 to the power of 1.5 times 10 to the power of 14. Then only the energy which you are putting in to raise the plasma's temperature as that requires energy, because if one particle will have 3 by 2 kT of energy. So if I confine n particle, 3 by 2 n kT will be the thermal energy which you have put in. Now, unless you get that much of energy from fusion, there is no point. Then there is no break-even. So that break-even condition is n times more than 1.5 times 10 power of 4. So the magnetic confinement, the n is small, like 10 power 14 or 10 power, because the gas. And confinement times have to be large. It will be seconds or sometimes even minutes. Then only something useful possible. And the problem is instabilities develop and the plasma will be lost. That is the problem. 80 years, it is not that people didn't do work, because India, we are not spending that much money on fusion research. But all over the world, USA, UK, France, China, they put a lot of money. So a lot of work goes on, but there is problem. Current status of MCF, time is over, 25. Okay, I will take 5 more minutes to. I will not go through what is the current status. It is given in the paper which I have quoted, 2023. If anybody is interested in paper, I have got it and I will cover. So you can read. The highlight is in 2025 they wanted to achieve break-even, but that has not happened. The joint European torus produced 63 megajoules over 5 seconds. That is the record now, as of today, 2020. More you can get from this paper, which I can hand over. About power as well. Doesn't matter. So the inertial confinement, what is done is you start with a curium tritium pellet, very small, micron size, and use lasers to implode the pellet to high density, and like 1,000 times. And when it is imploded, it automatically raises temperature because of PDV work done on the material. So reactions will start and the whole thing will disassemble. So you have to know the required energy within that confinement. There are 2 schemes which are used. One is to use lasers directly on the pellet and produce this implosion, increase in density and reaction. Other thing is use lasers to produce X-rays. X-rays are used to do the indirect drive. Indirect drive is more energy demanding, because first you have to convert laser to radiation, thermal radiation. So there is a efficiency. Whereas the direct drive is more energy efficient. And the highlight is that in the lab called NIF, National Ignition Facility of US, there they produce, they put 2.5 megajoules of energy from the laser and produce 3 point something megajoules of energy from, that is the highlight as of 20. So that is the, there also a reference is there, paper is there, they can hand over your interest. Thank you. Time in time. Yeah. Helium-3, of course, if you can, no, if you go to, the helium-3 can be used together with proton. There is another reaction where fusion can, but it will require much, will not be 80 type, not 5 kV to 10 kV, it will be welcome 100 kV. Okay, I was almost here.
Now, to express our gratitude, we would like to present a memento and a book titled On the Wheels of Education Serving USA and India, written by Professor C.V. Krishna, renowned scientist, to Dr. S.V.G. Menon by Dr. R.T. Varisa.
Thank you. Thanks. Everything because of you. All because of you.
Good afternoon to all. Our next presentation is by Professor M. Mustafa, who is presently Associate Professor in the University of Calicut. He took his PhD in 1997 from Aligarh Muslim University on the measurement and analysis of excitation function for some reactions induced by light and heavy ions. His research area of interest covers wider areas of experimental nuclear physics and application including reactor safety, radiation therapy, space radiation effect, and nuclear astrophysics. He is also collaborating with BRC Mumbai, Nuclear Science Center Delhi, and Variable Energy Cyclone Center Kolkata, and also with some international collaboration like IEMF from Italy. With immense pleasure, I invite Professor Mustafa sir for the speech. Thank you, sir.
Good afternoon. Fusion.
ലാപ്പ് ഇങ്ങോട്ട് എടുക്കാൻ പറ്റില്ല അല്ലേ? ലാപ്പ് ഇങ്ങോട്ട് എടുക്കാൻ പറ്റില്ല അല്ലേ? ഒന്ന് കൺട്രോൾ ചെയ്യുമ്പോഴേ കോർഡിനേഷൻ വെക്കാൻ പറ്റുമോ? പിന്നെ കോർഡിനേഷൻ കിട്ടില്ല, അതുകൊണ്ടല്ല കിട്ടോ? കുറച്ച് ചേഞ്ച് ചെയ്യോ? ആ മതി ഈ ചേഞ്ച് കൺട്രോൾ ആക്കാൻ. It's a huge thing. You know, our recent drive for installation of solar panels in our rooftops, you know, typically for up to 3 lakhs. And mostly for the installation of battery and other accessories. Okay. What lies behind this? First thing, you have to have a wider area if you have to happen to visit Cochin Airport CL, which is supposed to come to the earth, and sand and soil and all these things and plants, that will be completely cut in. That is the major, you know, the formation of our soil from the rocks, and the soils are being converted. Non-commercial wise, I mean, domestic wise you can have, in wide sense we are having this biogas plants, which may be feeders, I mean, adjustable. There are two advantages, adjustable. There are two advantages. The one thing is that we can discard our waste at the same time. We can discard our waste at the same time. We will get this energy. So we can support it. It becomes again a nuisance, but managing is not a problem if you are really interested. Then there is another mechanism again, which is still in the discussion. I mean, as a common facility, it is being generated. So the hydrogen is, you know, whenever there is attractive force, when they come together, there will be energy release. So when hydrogen combine, water molecule will be formed, from which the binding energy will be released. Typically, very small energy, you know, the molecular binding energy is only a generated per or specific energy is very small, but comparing the amount of hydrogen available with us, so it is a promising further into fragments of medium mass, so you can save typically 1 MeV per nucleon. So typically uranium you can say, particularly we say 230, generally we say 230, practically you can save typically 200 MeV per nucleon. Now if you have 1 gram of the sample, typically you will have 10 raised to 23, 24. Or if it is a heavy ion divided by 200, you can say that typically 10 raised to 21. So it is a huge number. So within 1 gram, you can have a large number of nuclei. Proportionally, you have happens a large amount of energy will be released while these nuclei undergo fission. So this energy will be released extending from the bomb. So to control this neutron number, and we generally use cadmium, and interestingly, cadmium is an interesting element. We say which is having better stability in terms of isotopes, and perhaps this setup only.
So you may explore why it is so. Okay. Depend upon this stability in terms of isotopic abundance and number. Okay. So by this, from microsecond to thousands of thousands. Throughout this period of his lifetime, until it is completely being converted into or decayed into stable isotope, it will go on emitting beta rays and gamma rays, which is a serious problem. Okay. How to tackle this emission of gamma rays and beta rays is the major concern for us. So any nuclei, they will be decaying. Proton-rich nuclei will be decaying by beta plus emission or positive emission or electron capture also. All the neutron-rich element, neutron-rich isotopes will capture. They will give you typically $82 gigajoule if it is being fragmented per second. And if this is being burned in one day as a whole, you can have continuously 1 megawatt continuously for a whole day with simply 1 gram of uranium-235. So if you have 1 kilogram, you can conveniently run for 3 years with 1 megawatt energy per day, or continuously for 1 megawatt. Now, the problem lies with the management of nuclear waste. There are two types of waste. Basically, the fuel waste, which is negligible, and apart from this, the reactor structural materials or source of combinations, they also will be exposed to this amount of radiation, including gammas, neutrinos, neutrons, and some alphas also, protons, etc. So maybe in lesser amount. So they also will be inducing radioactivity in the structural material. So managing this also is important. Though many of the isotopes are medically and industry important, all of them are not. So we have to transmute them into better, stable isotope rather than their routine beta decay chain by proper activation using base materials. So conventionally it was a thought of utilizing neutrons and protons, but as far as the heavy contributions, heavy fiber is concerned, it itself is neutron rich, so you have to have N2N type reaction to have diminished number of neutrons. Or PN reaction is an alternative, for the reaction cross-section is limited, activation, transmutation is also larger. Nothing is cheaper, simple. So we have better alternatives to use photon beam, particularly now we have having much cheaper Bremsstrahlung accelerators, most commonly used for medical purpose. You can have energy ranging from few MeV to typically 25 MeV, mostly medical purpose, by producing gamma N reaction primarily. There's a good potential and C chance, and then if it is desired, you can have gamma P also and other channels. So meantime, we just introduced you some of our measurements or analysis in this world. And first one, interestingly, it is technetium, which is an isotope produced as a nuclear waste, not directly, generally through molybdenum nandiers. This molybdenum is taken as source of ore, molybdenum milk also, we say, source of technetium, which is a most important isotope used for radiation imaging in hospitals for particularly cancer imaging. Now the problem is that molybdenum is successfully converted into technetium which is in excited state. The excited technetium is used for the imaging. Now, it is 140 kV gamma ray excited stage decay by emission of 140 kV, 142 kV, 148 gamma ray. So it will come down to its ground state. That ground state itself is also radioactive, but lifetime is extremely large. So it is a big nuisance. Now what we have proposed is that, so what will be the spend, and again, typically only 10% or less of the effective technetium is being properly or effectively utilized for imaging, because due to this half-life, you have to take larger amount and some of them will be unutilized again. So this decayed ground state technetium is also a major challenge. So what you propose that you collect all the technetium, whatever it is there, then excite it by simply using Princeton. So you can see up to 9 MeV you can easily irradiate. Beyond 9 MeV it will emit neutron. So you put a limitation. Then you can successfully convert this technetium ground state to ISM stage. So you can reuse it any number of times, whatever this spend and unspent, except the one utilized for the imaging, that is utilized. So that is a small portion. So that is an effective alternative. And we have tried another mechanism, just for other purpose, not directly related to this, that is the fluorine 18 is an important isotope that we try to produce from fluorine 19 by gamma P reactions, which is much easier and cheaper. You know, typically it is produced from oxygen 18s, which is much costlier in terms of isotopic abundance. So that is very, and tagging also very easy for this. And then just we have tried the radiation activated samples of structural material, for example, cobalt or iron. We have studied a series of samples. Out of this, we have this cobalt-50 gamma reaction we have studied. So these are, you can say tip of the iceberg, so we can have a right opportunity to express. We are also working on that. Okay. So I think this is the basic things I want to cover. You guys can skip this. So this is a typical comparison. You see the typical energy resources, specific energy output from various sources, and typically it is only, typically we say much less than 50 megajoule per kilogram, whereas it is almost 6 times larger for nuclear reactor. Still there is promising nuclear fusion, but it is still not under our control, and we are nowhere near the, though so many people claim it, still nowhere near the, our projects. So I think I can give you a glimpse of idea of the effectiveness of power plant and why we argue for this nuclear power plant. Okay. Thank you.
Thank you, sir. Now it's time to express our gratitude. I invite Dr. Tiwari sir to give this present, a memento and a book titled On the Wheels of Education Serving USA and India, written by Professor Sree Krishnan, a renowned scientist, to M.M. Mustafa sir. Sir, please.
Good afternoon. Our next speaker is Dr. Ryan Kumar, who is presently Assistant Professor in CUSAT, in the Department of Physics. He did his PhD from IIT Roorkee in 2015, and from 2015 to 2017 he was in Tata Institute of Fundamental Research as a postdoctoral fellow. Also he is a DSc Inspire Fellow in NIT Surathkal, Karnataka. And he has in total 16 publications. I invite Ryan Kumar sir for the speech. Thank you.
Thank you, sir. Thank you very much for this introduction. I will be speaking about some of the tools we are using in nuclear physics, try to understand the physics behind this kind of in nucleus. I am from Cochin University of Science and Technology. So currently it is 10th in public university as per our latest NIRF ranking. So basically they are very supportive also in research and related activities, and they have accredited with NAC A+ grade in our last NAC visit. So in 2024, the Nobel Prize was awarded for these two gentlemen, mainly Hopfield and Hindon, for their work related to artificial neural network, how they used physics to find the patterns within the data. So this Nobel Prize was awarded for their fundamental discoveries and inventions that enabled machine learning with artificial neural network. So what they basically did, they used some physics laws to understand the patterns within the data. So even though it was not related to nuclear physics or any other thing, in Hofmann's work, they were able to restore some of the, reconstruct some of the data, and in the case of Hinton, he was able to discover some properties or physics-related informations from the data and their interconnected patterns. So that's what we are using in our recent machine learning or in recent physics. We are using the same technology, but with a larger data or with a larger technical tools. So if you just imagine how our neurons work in our brain, just like in the same manner, whether the neurons are connected and they are transmitting the data. If we are studying, I don't know whether it's clear it or not, if we learn things, the connection between neurons will be strong and otherwise it will be weak. So in the same manner, how the neuron in humans work, in the same way we can create some nodes or artificial neurons to learn patterns from data, different data. So if we train properly, the connection between these neurons will be very strong, otherwise it will be weak. So in Hofmann's work, basically they have arranged they are giving some data to a system, and it's storing its energies as a value of values in energy landscape. You can see that graph there. So if we give data, the system is storing that all information and it's creating a pattern. So when you provide some disordered data, what is given in this input pattern, you can see in the right extreme right. So if you give some disordered or distorted pattern to that system, it will try to find the most appropriate minimum or its most appropriate position where it can be matched with our learned things. Basically, the system has learned something from its trained data, so it will try to match with the data what it has already provided. Then it will try to get an image which is, so this is, actually this is not working, or it's not able to see there in that very bright screen. So we can see that if we give a distorted data, it will give the most appropriate image which is suitable or which is similar to that data. In the same way as our artificial cameras are working now, it is just catching our number plate, car number plate of vehicle, and it will creating its own image. So in this field, there are some terms called artificial neural network or artificial intelligence, and as a subset of that artificial intelligence, if you are using some machine learning techniques, then we can say that machine learning is also a subset of artificial intelligence, and some more data are, large amount of huge data are available, then we can go to this deep learning calculation. So in principle, it's nothing but we are providing some data. The system will try to get some most appropriate fit to that particular system. So if, in a simple word, if I provide some data like this, it's a linear regression plot. So you have y equal to mx plus c, where m is the slope and c is the intercept. In the same way here, if we provide some data, we can see that different data are there, and the system will try to minimize its error so that it will calculate some mean square error, or there are some other terms also there, random root mean square values are also taken in certain cases. So you have some true values are there and predicted values are there. So these two things will, it will try to reduce the error function within this system. For that, we have to consider create some artificial neural network. So here xi, x1, x2, x3 are different inputs, and finally we have something called y. Finally we have something called y is the output. So we can relate these two things like this. Y is equal to, you can just think about this wx plus b, which is something similar to our mx plus c, the same equation, equation of a straight line. But when we consider a linear regression, it will always give a linear output. So in certain cases, we have to get some non-linear functions also. For that, we have to consider some functions called activation functions. That's what given by the sigma term. Sigma term is a non-linear function, something like a ReLU, sigmoid, different functions are there. People can use different types of activation functions. So the input xj is there, and it's connected to the other layer. There are different layers like H11 or H21, these are different hidden layers. So if more than one layers are there, then we can simply say that it's a deep neural network. The length, the depth of that layers are more. So that's what known as deep learning or deep neural network. So here xj is the input, and its input is appropriately modified based on the data provided to that system. And based on that, different weights and biases will be taken, and it will be trying to reduce the loss function or the error function within that data. So that's what actually happening. If we provide some data, the system will automatically create some pattern. Basically, we don't know what pattern is creating, but the output will be in such a way that the loss function or error function will be minimum. For any neural network, the error function should be very, very minimum. Then only we can say that our predictions will be better. So here, these are some of the results we some of the calculations we performed using deep neural networks. Here we have considered the binding energy per nucleon. So I hope all of you, the students, are aware of binding energy of nucleon. So here we have considered data from atomic mass table to 2016. So from that, 80% of data was used for training purpose. So we have to properly train our network. Then we used the remaining 20% for validation. Basically, we are checking our model, whether it's working properly or not. Because we know that what should be the answer for that 20%. We are just validating our model. So after that, at that same time we have to find the error function or loss function during this training process and validation process. So that's what given in the first table. Binding energy per nucleon 0.01 MeV is the loss function or error function. Error during that training process, and during validation it's 0.022. In the same way, we can calculate the binding energy and beta decay energy. We have also calculated the separation energy of proton, neutron, separation energy of 2 protons and 2 neutrons. So those details are given there, and with this data, we predicted our results, some of the results. So we know that while validating, we are providing some inputs. So the x-axis it's the true value, that means experimental result, and in the y-axis it's the predicted value. The neural network is predicting the results. So we can see that these two things are aligning in the same line. So it's able to exactly predict that results. There are some deviations are there in some of, and the magic numbers are also included as the additional, and the magic numbers are also included as the additional inputs. Beta decay energy അല്ലേ എനർജിയുടെ അല്ലേ beta plus and beta decay. Yeah, if it is an induced one, I think it's possible. It's like beta plus and beta minus for that. Plus and minus, yeah. But some reference. So yeah, I just so basically here the question is related to the x-axis, whether it's positive or negative, why it is positive or negative. Yeah, basically it's from that ME data only. We are taking the data points, so they may have some references like that. And in some of our research, yeah, in level density case also we got some negative values, but actually experimentally there should not be any negative values for level density. But data is already provided, even the PRC has published those results. So it's a combination of those data. Maybe some detector resolution issues or something like that. There is some spreading of data. Yeah. So this is related to AME 2016 data. Then we consider some typical examples also here. Some different selected isotopes are considered with the proton number 19, 52, 82 like that. And you can see that we have considered 3,000, more than 3,000 value for binding energy per neutron value, and more than 3,100 values for beta decay values. And when we consider this pairing and magic number cases, inputs in the input case, we can see exactly how this staggering in beta decay values are there, and how these binding energies are reproduced. And in here, the experimental value is the black dots or open circles, and the red one is the predicted values. So we are more or less able to reproduce these results, and similarly we did some calculation for separation energies, and in separation energy also during this magic number, you can see that how this staggering is pronounced, and there is some differences between separation energy in the case of protons and proton separation and neutron separation energy. Sorry, yeah. So when we train our model with the 2016 data, there are some data were not available for certain nucleus, but they were reported in 2020 AME data point reports. So we just try to reproduce those results, and you can see that it's able to exactly match in most of the cases. Only one or two results are varying. So it's able to, the model is able to explain the 2020 data with the 2016 data set. So these are some other examples for some of these separation energy calculations also reported here. And in the case of level density also, the level density is it's the number of energy levels per unit energy interval. So when you consider shell model calculations in liquid model, it's a macroscopic approach. But in the case of shell model calculations, there are different energy levels are there. So number of energy levels in an unit energy interval is known as nuclear level density. So as you provide enough energy, the number of levels will be more and more, and the level density will be extremely high, which cannot be experimentally determined straight away. So there are certain experimental techniques are there. Then experimentally they will try to understand the neutron evaporation spectra and try to get some information about the nuclear level density. But it's a very important tool or very important parameter in most of the statistical calculations, in experimental calculations. So the measurement of level density is a very crucial factor in these calculations. So in these calculations, we consider two different data sets, mainly lanthanide region and period 5 region. Mainly the data is available only in that particular two regions. If the data is not available, it's very difficult to get a proper training and get some proper result. That's what given there, and this is the loss function or the model giving some loss functions in these calculations, and these are some experimental results. So here the neural network is compared with an Oslo experimental Oslo data. Basically it's the experimental group. So those data are provided by these black dots, and the red one is the theoretical model. And we compare with the Hartree-Fock-Bogoliubov results theory just for any comparison. Certain nucleus are there and how these things are able to match, and in the lower mass region, lower temperature or lower excitation energy, you can see that there are some changes in this some zigzag minor pattern is there, which is mainly due to the shell correction effects and the pairing effects. So the pairing effects are actually playing very important role in this low temperature region. So these are some of our predictions and how experimental data the first one is SVR method. So these are different techniques how we can get some, try to minimize this loss function. So there are different type of regression methods are there. So here we try to understand the predictive, the Q value of alpha decay. So in the case of alpha decay case also, different approaches are giving. In earlier case we consider only one deep neural method, but now we are trying to incorporate some other regression methods where random forest approach and SVR methods are introduced, and in these cases our error function is very minimum in the when we consider the random forest approximation. So that's not given here. So in different isotopes how these methods are able to explain the experimental results. So the green dots are the experimental results, and the theoretical results are also able to match some of those results or give at least give some patterns there. Then this is some graph where we can see that how the half-life is plotted against the neutron number, and we can see that there are different magic numbers how the Q values or the half-life is showing some dips, and in our calculation we are getting something n equal to 184 is showing some kind of pattern magic kind of structure, and this is the importance of different input parameters in these calculations. And the first one is the Q value, which is playing a major role, and then is the neutron number, and proximity factor is there. And in this case, in the Q value of reaction, the alpha pairing term is not that much effective because it's related to the alpha decay, whereas alpha is the one of the strongest binding energy maximum for that particular system. That's why we are able to see some of the cluster or alpha decays in most of the systems. So they are the students working with me, Jyotish, and they are the PhD students, And Gokul and Asmita will be presenting their work here. So thanks to collaborators. I would like to thank our supporting funding agencies. So if time is there, I can move to some other thing. I don't know. Okay, then I'm stopping here. Okay, thank you. Yeah. No. No. Actually, one of the drawback, we can say, it's not a drawback, but we can say that in this model, in AI machine learning, actually we don't know how the system is predicting. It's like a black box. It's creating its own differential equations and mathematical connections in this. It's creating some pattern with this data, but we don't know exactly how it is getting that result. No, we don't know how it is working inside, but we have to give the data training properly, and we can give that, yeah, with these two inputs, with proton number, neutron number, this is the binding energy. We are giving those, feeding that data. Then if you are giving some unknown X and proton number and neutron number, it will generate its own binding energy. But we don't know how it is how it is connecting these two things. That's the beauty of this data. So if there is no sufficient data for training, it's very difficult. Its predictions cannot be reliable then. Yeah.
To find out there is a missing vector there. That's what I'm trying to say.
Okay.
Okay. So with this,
Thank you, sir. Now it's time to express our gratitude. I would like to invite Dr. Tiwari, sir, to give this present, a memento and a book titled On Wheels of Education Serving USA and India, written by Professor C.V. Krishna, renowned scientist, to Dr. A. Ryan Kumar, sir. Now, to honor Dr. R. Tiwari, chairman of this session, and Dr. Rajesh K.R., co-chair.
അത് കഴിഞ്ഞ ഒരുമിച്ച് ഇല്ല, നമ്മളങ്ങനെയല്ലല്ലോ ചെയ്തോടനെ. അല്ല, ആദ്യം മിത്തൽ സാറേ പറഞ്ഞു, പിന്നെ അത് നെക്സ്റ്റ് ഒരു ഓർഡറിൽ
അതെ ഐക്കൺ ചെക്ക് ചെയ്ത
Welcome back everyone. Hope you enjoyed the break session. Now we move on to the final session. First we have Sree G.D. Mittal sir, Secretary INS, on topic Indian Nuclear Society aims and objectives. Then Dr. G. Haridhar sir, Head Health Safety Section, Health Physics Division, Bar RCAT Indo, followed by Dr. P.M. Ravi sir, Alumni Bar. The session is chaired by Sree M. Bhaskaran, Senior Scientist, former Chief Executive HWB, and co-chaired by Dr. K.M. Manu, Assistant Professor, Department of Physics, Sri Krishna College.
Good afternoon, distinguished scientists, my colleagues, dear students. We are going to the last session of today's program. The session is chaired by Sri Bhaskaran Mandavur, Senior Scientist and former Chief Executive Heavy Water Board. Bhaskaran Mandavur has been involved with isotope separation process development, design and amplification, engineering, setting up of plants based these technologies and their operations close to 4 decades. He graduated from BARC Training School, subsequent to his chemical engineering from Government Engineering College, Thrissur, and joined Heavy Water Board in 1980. He superannuated from service in 2016 and was associated with the development works with the Heavy Water Board and Department of Atomic Energy as Raja Ramana Fellow for 3 years. He is presently having his retired life at Angamali with great pleasure, and on behalf of Sri Krishna College Physics Department and on behalf of INS and Atomic Retiree Association, I invite Bhaskaran Mandavur to handle the session. Our first presentation is by Sree G.D. Mittal. Sree G.D. Mittal, after completion of BSc from Agra University, he joined Metallurgy Division, Bhabha Atomic Research Center in 1967. His area of specialization was X-ray crystallography. He worked in post-irradiation examination division to study and analyze the spent fuel. In 1990, he was transferred to training division, now known as Human Resource Development Division. He was taking classes for nuclear physics experiment for engineers and physics training officers. Besides, he had been counseling the trainees in their personal matters. During his 12 years stay HR duty, he was in charge of written test for entrance examination for training school. He retired on superannuation in June 2002. Post-retirement, he worked in private companies, was in charge of training in HR, training in nuclear subjects, networking with Indian industries associated with nuclear projects. He had been associated with the Indian Nuclear Society since its inception in 1987. He had provided support to all INS executives and trustees in INS formative years. Due to his flair in maintaining the accounts of society, he was elected as treasurer of INS Executive Committee in 1991 and continued to hold post of treasurer for 18 years at different periods, and was also the secretary from 2003 to 2007. At present, he is the secretary of INS EC since December 2022. His dedicated service to the Indian Nuclear Society got him an INS Special Meritorious Service Award 2006, which carried a cash prize and citation. With great pleasure, I invite Sree G.D. Mittal to deliver his talk on Indian Nuclear Society aims and objective. Please, sir.
Bhaskaram sir, thank you very much. My colleagues in BRC and DAE, my young children, friends, it is my privilege to present my society which is sponsoring this program, Indian Nuclear Society. See, as lower bottom is Anu Manav Sevartham, that is self-explanatory for human mankind, atomic energy. This one. So, it is very simple address, Indian Nuclear Society, Anushakti-Nagar, Mumbai, but to be very clear, Project Square is also added. Our email address you can note down, indiannuclearsociety@gmail.com, and website is www.ins-India. This is quite informative. And we also have a YouTube where you can find not many lectures and other information. The objective of the societies are, see, you read carefully to promote the advancement of nuclear science, engineering and technology related to atomic nucleus and of allied sciences, to aid in the integration of several disciplines constituting nuclear science, engineering, technology, to encourage research in nuclear science, engineering, technology, technology and allied fields, to establish scholarships, grants and awards, to hold meetings for the presentation and discussion of scientific and technical nature. This today's program comes under that. To prepare and disseminate information related to nuclear science, engineering and technology through journals, books, pamphlets, reports and other information media appropriate to a scientist. To cooperate with the government agencies and to engage in nuclear science activities. This society is registered with the Registrar of Societies and as public trust also in January 88. See, this was our first inauguration of the society, which was inaugurated by J.R.D. Tata. And Dr. M.R. Srinivasan, who was then chairman AEC, was chief guest. This is the photo of that function. And in this, Dr. M.R. Iyer, extreme side, J.R.D. Tata, M.R. Srinivasan, P.K. Iyengar, and you know, a young fellow at that time, Kandan Iyer, who was very young at that time, now he is professor at IIT Jammu. You know, this is very important. While inaugurating, J.R.D. Tata said, the society can go a long way if it is able to dispel irrational thinking among intellectuals and the public that atomic energy is only to develop atomic weapons. So, you know, a industrious person talking that it can do a great thing if it is able to dispel irrational thinking among intellectuals. This was the news heading at that time. We have 5 branches at Rawalbhata, Rajasthan, Kalpakam, Hyderabad, Narora and Mysore. These we have the award scheme to fulfill that objective. So lifetime achievement award 2,50,000. Then for meritorious scientist 1 lakh. INS Industrial Excellence, silver plate and citation, and for young scientist medals, and for science communication also 1 lakh, and to eminent scientist award alone overall world over 1 award. This was our first award where Prime Minister at that time, Bajpayee, was honoring M.R. Srinivasan. Then it was at Kalpakam where Dr. C.V. Sundaram was awarded by President Abdul Kalam, and Dr. Chidambaram is standing beside him. Dr. Iyer was awarded by Al-Baradi, who was IAEA chief at that time. Prime Minister Manmohan Singh awarded V.K. Sharma in 2005 conference. Then Dr. Chidambaram himself was awarded by, I'm forgetting him. Yes. And then P. Ramarao was awarding scientists. Then this is very interesting. You know, in center, George Almodias, he was attacked. I mean, when Bombay blast was there, he was staying in Taj Hotel. And luckily, our police rescued him by climbing ladders and all those things. So he was survived at that time. Same out. Then afterward there are many chief guests, so I don't want to talk too many things. Then we had industrial training program, like pressure vessel and pipe design. These were basically for scientists and engineers who want to get very special knowledge for their own career. So 5-day courses were conducted in these are the courses. This is how we grew the funds. And if you see, there was a plateau. So that is not a good sign for INS. But now anyway, in latest balance sheet, we could increase the funds. We have the newsletter and very quarterly newsletter. These are all available on the INS website. We had recently international conference in 2023. Then recently we had an annual conference in 2024. Our executive committee consists of this. This is the information you should keep, and national flag hosting, etc. What about it? Thank you very much. Just 2 more minutes I will take. This was my photo in the last conference when Putti arranged at UC College. So I was there. As far as this PPT is concerned, my talk is over. But I want to add some points for my young engineers and scientists. See, the curiosity part of the scientist should remain. So you should be curious, but simultaneously doubt should be clarified. And if you are not able to clarify, best thing is apply common sense and sometimes believe. See, this is a place of Guruvayur. Now, an idol worship, most of the fellows who apply logic can't justify. But then we worship and God is there. My own example, I was not to come. I decided when Putti told me that program is there, so I decided with my wife, we are going whether Indian Nuclear Society is sponsoring or not. And we came. So that is something you can't explain in simple language. I saw day before yesterday, so much crowd. If you apply a little logic, nobody can explain that. Why we are seeing the goddess or God or sitting on the elephant, just apply your logic. And you can't explain. Here, another thing, I don't know why my at least 20% friends are from Kerala. So many friends. I myself not able to explain. This is one reason that I could think of. You people are very sweet. I honestly feel when I analyze this, one thing, those who had been in Mumbai, they learn local language. I myself not able to learn in 58 years Marathi. But all these Kerala fellows sitting here, they know Hindi, they know Marathi. Not only that, they teach their children local language. They talk in there. So this is one of the reasons I could think of that Kerala fellows are very sweet and I am thankful to you all for this. And then, please note down the email address. My PPT is here only. Lot of questions can be answered, and whenever you feel are not answered, Govindhan Kutty and his friends are there, can explain, and we are there at your service. Thank you very much.
Thank you, sir. Now it's time to express our gratitude. I would like to invite Sree M. Bhaskaran, sir, to present a memento and a book titled On the Wheels of Education, Serving USA and India, written by Professor C.V. Krishna, a renowned scientist. Sir, please.
Thank you. Yeah. Second. Who you want to take this book? Should be read. Okay. You share with your friends.
Next presentation is by Dr. Haridas Ji. Dr. Haridas Ji has completed his MSc Physics from Mahatma Gandhi University, Kerala, and completed his PhD in Physics from Devi Ahilya Vishwavidyalaya, Indore. He joined BARC Mumbai in year 1988. At BARC, he was mainly responsible for radiation safety aspects of the commissioning and operation of heavy ion accelerator at the Tata Institute of Fundamental Research, Mumbai. Later on, in 1992, he moved over to Raja Ramanna Center for Advanced Technology to look after the radiation safety aspects of the synchrotron radiation sources of the country, Indus 1 and Indus 2, which are the largest accelerators in India. His area of research interest is high energy radiation dosimetry in particle accelerator environments. Indian Association of Radiation Protection has awarded him the Dr. A.K. Ganguly Felicitation Award for the Best Operational Health Physicist in 2010. In the year 2014, he has been invited by IAEA Vienna to deliver a talk on challenges in occupational radiation safety in particle accelerator facilities. Department of Atomic Energy has awarded him 10 Group Achievement Awards in recognition to his service to various projects of the department. In 2022, he was invited by IAEA to South Korea as an expert from India to discuss the radiation safety aspects and guide them. He is also the Radiation Emergency Coordinator for the Madhya Pradesh region for responding to any radiological and nuclear emergencies in the public domain. Presently, he is an officer in charge of Health Physics Unit, Raja Ramanna Center for Advanced Technology, and Head Health Safety Section Accelerators, Bhabha Atomic Research, Mumbai. With great pleasure, I invite Dr. Haridas Ji to deliver a talk on nuclear radiation safety. Thank you.
A very good afternoon to all of you. In fact, I am very thankful to the organizers, especially the Atomic Energy Retirees Association. I mean, normally when we think about retirees, they used to remain silent and do some other activities and all, which is of their interest. But these retirees are so active, and I am very happy that Praveen Kumar ji, he has called me at least 3 or 4 times to discuss about this thing, and Govindhan Kutty sir was constantly in contact. But I was wondering that how I was invited, because from my biodata which was read, it is all accelerator. I said nowhere nuclear safety is coming in the picture. Anyway, with this
a brief introduction, but I will not go into the more technical details about the issues, because what I find is that there are many students here which they may have, because the speakers who have talked about in the morning, they were all talking about the nuclear energy protection, what are the problems, things like that. What are the options available? Of course, I have also included in my talk, but most probably I will not talk about that. It's a sort of repetition. But one thing is that when we talk about, Dr. Malhotra also, when he talked about the nuclear energy program in the morning, extempore speech, a fear of radiation people have in their mind. Yes or no? You have to either raise your hand or, yes, students say, why we are talking about all these things? You have a fear about radiation? No. Yes or no? Yes, but haath uthaiye, you raise your hands. Yes. But why this fear? Why this fear? If there is a fear, there should be a reason for that. Without any reason, there is no fear. There is no meaning of fear. Maybe I will touch upon these aspects, which is very essential. So, without taking much time, I will proceed to that. So these are the topics which already have covered. So where is the pointer? Pointer is not over. Okay. So purposefully I put the first three bullets in black, which I will not be talking much about that. I will be focusing on the other part. So this also you have heard. Maybe a couple of slides I will show about this global energy scenario. You can see that the nuclear in globally, it is 14%. With the total nuclear production across the world, if you see, the nuclear is 14 and remaining 42 is, the major chunk is coming from the coal. So now coming to the Indian nuclear energy scenario, you can see that nuclear portion is nearly 2 to 3%, not more than. Now there is a very, and we have maximum from thermal, something around 63-60% is from thermal. That is the whole issue of carbon emission, the global warming, etc. is coming. Now a very important figure which tells about the human development index. So when we talk about the electricity generation, why this electricity generation is required, it's a very important factor to be kept in mind. So by our government of India has decided that by 2047 we have to develop, or we have to declare India as a developed nation. Now how do you declare a country as a developed nation? If the country has got a human development index slightly above 0.8 or 0.9 or close to 1, you can say that the country is developed. So now what are the parameters which tells or which takes the human development index to 0.8 or 0.9? You can see the x-axis is the per capita power consumption. And you see the red line which is parallelly drawn along the x-axis at the top at 0.8. Above that line you can see many countries, Germany, South Korea, USA, Norway, UAE, Qatar, Iceland, etc., etc. They are all developed nations. Their human quality index is more than 0.8. Now, you see the per capita power consumption in those countries, they are more than 5. So now we in India, we are about 1.5. So if you want to develop, if you want to declare it as a developed nation, then we have to shift that yellow arrow you can see. You can shift the per capita power consumption to nearly 4.55, so that we will be able to reach the Human Development Index to 0.8, then we can declare it as a developed nation. Now, how to achieve this? You can see that this is the installed capacity of our Indian nuclear power program, where by 2047, on the y-axis you see 2042, 2047 when it comes, the present rate of growth of electricity, if it goes at that rate, we'll be having a shortfall of around nearly 70 gigawatt. So this shortfall, we have to fill it up. And for that, what are the key factors which are required? The key factors which are required are, one is go for renewable sources of energy, including the nuclear, and you have to go at a rate of 4 gigawatt per year. Now presently it is maybe 0.2, 0.3, something like that, 0.3 gigawatt per year. From that we have to go to something around 4 gigawatt per year, that is around 20 times increment we have to achieve within this is 2025, within 23 years we have to achieve this much. That's a very big challenge. And that is one thing. The second thing is the Paris Agreement, of all of you have talked about, so I will not go into the detail of that. See, we have to minimize the temperature increase within 2 degrees because of all the emissions. So we have to do all possible means by which the emission can be controlled, or whatever emission is there, that should be trapped. Now I will come a little bit about the possibilities, that is the nuclear fission. I have just purposefully put it just for the students because all the BA people know about this thing, students also know that, but there is one interesting fact in this. These two German chemists, Otto Hahn and Spatzman, on the left and right, they have got simple experiments they did, and they found out and they bombarded uranium with neutron, they found some barium, some material they found, but they were not able to explain that. They found barium is formed, some heavy elements are formed, but they were not knowing why it is happening and what is happening. But this lady, Meitner, she only explained during a morning walk. She is an Austrian physicist, chemist rather. In a morning walk, he was discussing with the fellow scientists that probably this may be because of the oscillation set up in the nucleus, like a liquid drop, and they accepted that. Unfortunately, this lady, Nobel Prize 1944, it was given to Hahn for the rise in chemistry, but not to her. Actually, fission was explained, discovered by those guys. They observed it, but it was explained by this lady. So this history is always fascinating and interesting. Fission, of course, you all know that this is a liquid drop model. I will not go into the details of that. The last one, you can note that why this is very important. 1 kilogram of uranium-35 is equivalent to 1,000 ton of coal. So you can understand that the energy potential which is available in uranium. And fission chain reaction, of course, in a nuclear reactor, the fission chain reaction take place. As all of you know that one neutron will make fission with 2 neutrons or 3 neutrons. These 3 neutrons will produce further fission, that is 2 raised to 2, 2 raised to 3, 2 raised to 4. Like that, the number of neutrons keeps on multiplying, and the fission per fission 200 MeV. So you can, enormous amount of energy is. Suppose if it is not controlled, then what result is in the right side is the bomb. When we talk about nuclear bomb, this is what is happening. So in a reactor, what happens? You have a controlled nuclear reaction. That means all the neutrons are not allowed to do the fission, but some neutrons are removed. You have a control. So this also previous speakers have explained in detail. Of course, you all should know that in a reactor, in a nuclear reactor, that there are some factors called K factor. It's very famous. You might have heard that in newspaper the news item comes that the reactor goes critical. So what is critical? So critical means the K factor. I will come in the next slide, details about that. Some factors are there like number of neutrons produced per neutron absorbed, fast diffusion factor, escape probability, thermal neutron utilization factor. And if this K is equal to 1, then we say that the reactor is critical. Okay? Reactor is critical. And if it is greater than 1, we say that it is supercritical or it results in an atomic bomb. Now, interestingly, we have many reactors operated in our country. These are the list of that. Sorry, this is in the world scenario. You can see that India has got 24, of course now one more is added. Last week one more is added. We have 24 reactors operational with a capacity of percentage of 2.4, but you can see Canada, France is the one having the highest. And of course this is Indian, this is the details about that. You can take if somebody is interested, you can take that. So now these are the plants which are under construction. Somebody was telling that every year 700 megawatt is being added. So now this RAPS 7, which was listed in the this thing, when I prepared this thing, it was not declared. But last week it was declared as that is also commissioned. And it is, the power is added to the, connected to the grid. Yes, this is the latest 17 March 2025. This is the news from Nuclear Power Corporation of India. Now, this also, I may skip, I will, okay. Actually, morning it was told that Dr. Homi Jahangir Baba, in the late, 1950s and early 60s, he only suggested that we have got a lot of thorium resources. And that should be utilized. And you can see that in this is the thorium resources across the world, total, and if you compare, India has got 9,63,000, which is around 50% of the world storage. So India has got 50% of the world thorium resources. Why don't we use thorium for that? Now, for that, 3-stage nuclear program was envisaged. First, natural uranium. Second, from the natural uranium, what we get is uranium-235 to plutonium-239. Plutonium-239 is used in the second stage, and thorium is converted to uranium-233, which will be, because see, there are two terms. One is the fertile fuel and fissile fuel. Fissile fuel is the fuel which can be easily, you can undergo fission, you can make it undergo fission. But fertile fuel cannot undergo fission very easily. So you have to convert the fertile fuel to fissile fuel. So this thorium which we were talking about, thorium-232 is not a fissile material, but it is a fertile material. So that has to be converted, that thorium has to be converted into U-233 by certain reaction. I have given the reactions here, which is called the breeding reaction. The thorium-232, when it is interacting with a neutron, it converts to thorium-233, then it decays to tractinium-239, and ultimately it comes to uranium. So you are converting a fertile fuel to a fissile, and then use that fuel in the reactor. So this is the 3-stage program, which is, and there are many reactions here. I don't go into the details of that, which are important in radiation safety in nuclear power reactors. I would like to mention here one. You can see that the fourth one from the bottom, the red one, cobalt-59, because when we were talking about the applications, you see many hospitals use nowadays radiation therapy for cancer treatment. And this is the reaction how that cobalt-60 is produced in a reactor. Cobalt-59, which is a stable isotope, allow it to bombard with a neutron in a reactor, and then it will get converted into one neutron will get added up, the proton-neutron ratio will get disturbed, and once you are disturbed, then once the nucleus is disturbed, it will decay. And that decay, it has 1.17 and 1.33 MeV gamma rays are produced, which are used for cancer treatment. Like that many, and in nuclear reactor, there are many fission products. I think, see uranium, when it undergoes fission, it undergoes in something around 40 types. So a lot of fission products will be formed, and in the coolant also there are many activities which are produced. They are all give rise to certain amount of hazards to working people. So now coming to the fundamental safety objective in a nuclear reactor or for any radiation facility, what are the fundamental objectives? Because see, any activity if you carry out, suppose if I am sitting here, I am standing here, I mean, that does not mean that I am not at risk. Maybe this may fall down. While driving a car, I may meet with an accident. So every activity is associated with a risk. So similarly, and that risk has to be mitigated. So fundamental safety objective is to control the radiation exposure so that unwanted exposure should not be experienced by working person. Control the release of radioactive materials to the environment. Restrict the likelihood of an accident. Then mitigate the consequences if such accidents take place. And now for that, we have a defense in depth mechanism. Suppose here if the power goes, you need to have a backup for that. A battery system should be there, something like that. So here you can see that the center black thing, which is the fuel, that itself is a layer, it's a physical layer, which will not allow the radioactivity to come out. And suppose if it fails, then you have another, which is the clad, that is around surrounding material, it will protect. Then you have a primary heat transport, because when the heat is generated, you are allowing the coolant system or the light water or heavy water, whatever depending upon the type of reactor, it will pass through the coolant. There is also a metal tube. So again there is a barrier, physical barrier, and outside that you have a vessel where the complete reactor is enclosed. I mean the core is situated. Then you have a shielding, physical shielding, and then you have a containment. So if one fails, the second takes care of, the second fails, the third takes care of, all will not fail. That possibility is not. So this is the way in which defense in depth mechanism is implemented. And in our nuclear power plant, especially the present system we have, around the nuclear power plant, 1.6 kilometers is an exclusion zone. No activity is permitted in that. Then you have emergency planning zones, radiological surveillance zones, etc., so that in case of an accident, public will not get affected, though we have the defense in-depth mechanism. Now, Dr. Ravisari is sitting here. The entire lifetime he has spent in these environmental survey laboratories, because each nuclear, but see how much atomic energy department is spending energy, technology, and the brain in protecting the environment and the public. You see, there are many ways in which the radioactivity can reach public. Like it can come to the water bodies, it can through atmosphere, it can come through inhalation to human, and it can come to food, then through vegetations, and then ultimately when we eat the grass, the vegetables or the animals when they eat the grass, ultimately it will come to us. So these are all the pathways from where one can get radioactivity in case of an accident. So what we have to do, we have to have an environmental sampling program or surveillance program. I think he may talk a little bit about that. Around the nuclear power plant, there are areas where this environmental sampling is done, where you sample, there are indicators, grass, soil, sediment, goat, thyroid, vegetation, food, water, all these things are analyzed in very high-tech detecting systems, and continuously it is reported to ensure within 30 kilometers, to ensure that there is no unwanted release, there is no hazardous release to the environment. Okay, these are some of this thing, radionuclear analyze. Now, coming to the safety statistics or status of Indian nuclear power plants, you can see TAPS, RAPS, that is Tarapur Atomic Power Station, Rajasthan, Madras, like that. You see the regulatory limit, because when you drive a vehicle, it is written that the RTO give instruction that is 40 kilo, not go beyond 40 kilometers per hour. So similarly, there are some limits which are prescribed by the regulatory authorities. The regulatory authority says that there should not be not more than 1000 microsievert per hour, or you forget about the sievert or whatever it is, some unit. It should not be more than 1000 microsievert or 1 millisievert per. So now see all these nuclear power plants, the emission or the annual radiation dose coming from these nuclear power plants are, you can see that it is something around 20 to 40, not even going up to, this is the actual measured data. Then now, one very good example from the Kakrapar Atomic Power Station, you can see before setting up a nuclear power plant, you need to have a baseline data of the radiation level in that area, right? And once the plant goes into operation, and due to the operation, whether is there any increase in the radiation level or not, that is monitored continuously. So this is the data of, you can say that 1988 to 2020, pre-operational and operation. See, maximum it is coming to around 600 microsievert, not even going up to 1000. So this way, there are many emergency scenarios are there, which are to be taken, like site emergency, off-site emergency, that in case of emergencies take place, what action has to be taken. Okay, now what mitigation measures are, okay, that you have to allow sheltering of people, you have to, in case of a nuclear emergency, you have to evacuate people, evacuation, you have to shelter them in a proper place, and prophylaxis. Prophylaxis means, as I showed, many radioactive isotopes which are released, in which iodine-131 is a fission product which is released to the environment in the form of a gas. If you inhale it, that goes and deposits in your thyroid. Thyroid is the critical organ for that. So, but in prophylaxis, in a nuclear accident, what is given, instead of getting a radioactive iodine going and depositing in your thyroid, you will be given normal iodine, so that normal iodine will go and saturate your thyroid, so that even if you inhale radioactive iodine, it will not go and deposit in your thyroid. So this type of measures are normally taken. There are monitoring of occupational regulations I have already told. Nuclear emergencies, this also has been talked about in the morning there are 3 nuclear accidents which can list. One is the Chernobyl accident. In fact, 31 people died in that accident. It is basically that accident has taken place because of a human error, not because of the reactor or this thing. It's because of a human error. That itself is a 1 hour talk, so I will not go into the details of that. So, but in 3 Mile Island, there is no death, but there was in Chernobyl, a lot of release of radioactivity took place, but here that also did not. In Fukushima, again, there was no death, but around 2,000 people died because of other reasons, not because of radiation. So now you can see that fatal accident-free operation in Indian nuclear power plants are experienced from we have started the activity in 1969. During 55 years of operation, we never had any fatal accidents in our fatality statistics also. I think someone was telling just before my lecture that see nuclear, only one, this is the nuclear, but the other hydro, oil, coal, natural, you can see it is order of 2 to 3 order high. Now the fear is coming basically because of this Nagasaki, Hiroshima bomb. Maybe 2 minutes, sir. 40,000, in 1945, 6th August and 9th August, 2 bombings took place, one in Nagasaki and another in Hiroshima, where 40,000 and 80,000 people killed. And people have fear of radiation mainly because of this thing. Now you can see that from radiation only 15% of the people died. Mainly it is because of the blast and the thermal wave which killed the people. Now, it's very interesting to know that, see, our human body is a radioactive source. How many of you know about that? Our human body contains radioactive isotopes. We are always, I will go into this straight away. See, 360 million atoms of radioactive potassium-40 decays in our body per day. You know, potassium-40 concept is a primordial isotope which has started its journey since the birth of the universe. From that time onwards, this potassium-40 is there. It is from banana, from green vegetables, all this potassium-40 is there, which when you consume, it will go and deposit in your body. And you know what is the half-life? 10 to the power of 9 years, billion years. It was there, it will be there, it is there, and it will be there. 2.5 million cosmic ray neutrons penetrate our body per day. Without knowing, if you are sitting here, the radiation which is coming from the upper atmosphere, when they enter into the atmosphere, it undergoes a sort of shower. That is, you might have studied primary cosmic ray shower, then secondary cosmic ray shower. Ultimately, when it comes to the earth, it is bombarded. We are bombarded. 2.5 million cosmic rays. 10 million secondary cosmic ray particles penetrate our body. I just wanted to say that we are all born with radiation and we are all compatible with radiation. So why to have that worry? Now you can see that a person who are receiving the radiation dose, around 80% is from the natural source. Around 19% you are getting from the medical exposures. That sir was telling that medical, if you go for X-ray, if you go for a CT scan, you will get something around 20 to 30 millisievert, which is a limit, which is more than the limit of a public dose. This is from the unscared data. Now coming to the cancer, because people have this fear about this cancer. This is an unscared report. It's an extract from the unscared is the United Nations Scientific Committee for the study of the effect of atomic radiation. They are scientific people. In Kerala, they did a study in which you can say that the last one, where they studied from 1990 to 1996, the cancer probability compared with other people, control group. They say that the data on cancer incidence and cancer death were collected during 1990 to 1996, and the preliminary study did not reveal any increase in cancer incidence due to the level of external gamma ray. Because there are some area where in Kerala, Brazil, some area where natural radiation is very high. But people are striving. There is a very interesting study which is coming up, that is the radiation hermesis, which I think Ravi sir will be talking in slightly more in detail. You can see that the right side curve, one is a linear one, because we know that after certain amount of dose, there is a problem. But below that, we do not know. So the international authorities, they simply extrapolated back, or telling that where we do not know, there also it is linear. It is what is called linear non-threshold model. But now, recent studies says that, there are a lot of studies, thousands of studies are coming up now, which says that at the lower, the blue curve, at the lower dose, there is the cancer risk, one is in the upper direction, that is the positive, the negative you can say, and the reverse direction, there is a positive impact. That means the risk reduces. of course, I have not included in Japan. They have done a lot of study. They say that at the low dose exposure, see, our body keeps on mutating. The mutation is taking place all the time. I also have a cancer cell. You also have cancer cell in your body. But what does it prevent? Who prevents the cancer cells to, don't multiply it? Please take it from me or maybe from my studies. It is only and only the immune system. Our immunity only helps. No other thing can help. There are machineries in our body to detect the cancer cells and destroy it. And to maintain that immunity, we have to do certain things, which so these are all the things. In fact, most of the developed countries, yes, most of the developed countries have accepted this except USA. I think I am almost over. These are the limits I have already explained. And summary. Now, among the energy sources, undoubtedly nuclear power offers sustainable, clean energy for tomorrow. To achieve the developed nation status, the total power generation to be boosted up to 100 gigawatt by 2047, that is at the rate of 4 gigawatt per year. Unwanted fear of radiation deaccelerate the progress of fast growth of nuclear power. More such awareness programs are required. I think Kuti Saab and your team may take it further forward. Stringent radiation safety norms needs to be revisited based on the recent findings on the beneficial effect of low level of radiation exposures and lack of scientific data supporting the LNT model. Robust nuclear radiation safety systems are in place, such as prior radiation safety assessment and analysis, shielding, detection, environmental surveys, emergency management, regulatory control, etc., paved way to fatality-free nuclear plant operation in India since last 55 years. So with this short thing, I conclude my talk. Thank you so much.
Thank you, sir. Now it's time to express our gratitude. I would like to invite Sree M. Bhaskaran sir to give this present, a memento and a book titled On the Wheels of Education, serving USA and India, written by Professor Sree Krishna, a renowned scientist, to Dr. G. Haridasan sir. Thank you, sir.
Good afternoon. Today's last presentation will be by Dr. Sri P.M. Ravi. Actually, it was decided to deliver a talk by Dr. Mahadeva R. Iyer, but his health condition is not so good. So, in his absence, Sri P.M. Ravi will deliver a talk. Dr. P.M. Ravi is the former student of Sri Krishna College, Guruvayur. He retired from Baba Atomic Research Center as head environmental section. Currently, he is working as a vice professor, Center for Advanced Research in Environmental Radioactivity, Bangalore University. He was a Marie Curie postdoctoral fellow of European Commission, worked at Bordeaux University, France. He served in various committee atomic energy regulatory body, India. With warm regards and with great pleasure, I invite Dr. P.M. Ravi to deliver a talk on public awareness issue and environmental radioactivity.
Good afternoon to all of you. Holding people after 4 o'clock or 5 o'clock, after a hectic scientific program, it is a very important, very difficult task. So I am given the task of this. This task is much more difficult, mainly because I am presenting somebody else's thoughts rather here. Now, why I am connected with Dr. Mahadeva here is, he is my great guru. He was my, I did my PhD under his guidance and a mentor and whatnot. He is everything for me, rather. And what is the connection between Sree College and me? And I am a former student of this college. I had my BSc. 50 years before, I was sitting like the place where you were sitting and listening to this type of lectures. And I'm extremely happy to be here, and it is a nostalgic for me. Incidentally, is there anybody who doesn't know Malayalam here? Everybody knows Malayalam. So why not I should talk in Malayalam? Malayalam ഒരു കുഴപ്പമില്ലല്ലോ. അപ്പൊ ഈ മലയാളത്തിൽ അപ്പൊ നമ്മുടെ പ്രധാന ഇഷ്യൂ ഇവിടെ പബ്ലിക് അവയർനെസ് ആണ്. ഇപ്പൊ പബ്ലിക് അവയർനെസ് പബ്ലിക്കിന് മനസ്സിലാവുന്ന ഒരു ഈസി ഭാഷയിൽ പറയുന്നതല്ലേ കൂടുതൽ നല്ലത്. വിത്ത് ദ പെർമിഷൻ ഓഫ് ദി ചെയർ ഐ എം ടോക്കിംഗ്. ഓ സോറി സർ. So you are a BA person, so what I am telling may not be that important because I'm rather, I may not be new to you, so I'm my target audience are students. Okay, thank you. So, അപ്പോൾ മലയാളത്തിൽ പറയാം അല്ലേ? നല്ല തൃശ്ശൂർ ഭാഷയിൽ നമുക്ക് മലയാളത്തിൽ തന്നെ പറയാം. അപ്പോൾ ഞാൻ എൻ്റെ ടോപ്പിക് എന്താണെന്ന് വെച്ചാൽ ന്യൂക്ലിയർ എനർജി ഫോർ സസ്റ്റൈനബിൾ ടുമോറോ. ഓഫ് കോഴ്സ് ദർ ഈസ് എ present topic which the seminar is being dealt with, and I will be talking about the public awareness issues on environmental radioactivity. In fact, നമ്മൾ ഈ ന്യൂക്ലിയർ റേഡിയേഷൻ, ന്യൂക്ലിയർ പവർ എന്നൊക്കെ പറയുമ്പോൾ നമുക്ക് ഏറ്റവും ആദ്യം നമ്മുടെ മനസ്സിൽ വരുന്നത് എന്താണ്? ന്യൂക്ലിയർ ബോംബ്. അതുകൊണ്ടുണ്ടായിട്ടുള്ള ഡിസാസ്റ്റേഴ്സ്, ലോട്ട് ഓഫ് ജനറ്റിക് ഇഫക്ട്സ്, ഒരുപാട് ക്യാൻസേഴ്സ്, നമ്മൾ ഒരുപാട് ചിത്രങ്ങൾ കണ്ടിട്ടുണ്ട് അല്ലേ? ഹിരോഷിമ നാഗസാക്കിയുടെ നമ്മൾ ഇത് കേട്ടിട്ട് എവറി ഇയർ ഹിരോഷിമ നാഗസാക്കി ഡേ ഇസ് ദർ അല്ലേ? അതിൽ നമ്മൾ പ്രൊസഷനൊക്കെ നടത്തും, എന്നിട്ട് ആന്റി ന്യൂക്ലിയർ എന്നൊക്കെ പറയട്ടെ അല്ലേ? പക്ഷേ നമ്മൾ ഇതിനെപ്പറ്റി ചിന്തിക്കാറില്ല കൂടുതൽ. ഒരുപാട് ആൾക്കാർ ക്യാൻസർ ട്രീറ്റ്മെന്റിന് റേഡിയേഷൻ ഉപയോഗിക്കുന്നുണ്ട്. നമ്മുടെ ഒരുപാട് ഇൻഡസ്ട്രീസിൽ റേഡിയേഷൻ യൂസ് ചെയ്തിട്ട് നമ്മൾ കണ്ടീഷൻസ് ഓപ്റ്റിമൈസ് ചെയ്യുന്നുണ്ട്, പ്രൊഡക്ടിവിറ്റി കൂട്ടുന്നുണ്ട്. പിന്നെ അഗ്രികൾച്ചറൽ പർപ്പസ് പ്രൊഡക്ടിവിറ്റി, നമ്മുടെ ഇന്ത്യയിലെ പ്രൊഡക്ടിവിറ്റി, അഗ്രികൾച്ചർ പ്രൊഡക്ടിവിറ്റി കൂട്ടാൻ ഒരു പ്രധാന ടൂൾ ഈ റേഡിയേഷനാണ്. റേഡിയേഷൻ മ്യൂട്ടേഷൻ ഉപയോഗിച്ചിട്ടാണ് നമ്മൾ ഇതൊക്കെ ചെയ്യുന്നത്. പിന്നെ വേറൊരു കാര്യം, ഇപ്പൊ ഹൈലാൻഡ് ഓൾസോ മെൻഷൻ ഇൻ ഹിസ് ടോക്ക്, അതായത് നമ്മുടെ ചുറ്റും റേഡിയേഷനാണ് അല്ലേ? നമുക്ക് ചുറ്റും നമ്മൾ കാണുന്ന ന്യൂക്ലിയർ സൺ, സ്റ്റാർസ് എല്ലാം ന്യൂക്ലിയർ റിയാക്ടേഴ്സ് ആണ്. ഐദർ ഫ്യൂഷൻ ഓർ ഫിഷൻ ആണ് നടക്കുന്നത്. പിന്നെ ഒരുപാട് റേഡിയേഷൻ അതുകൊണ്ട് നമുക്ക് സ്ഥിരമായിട്ട് കിട്ടുന്നുണ്ട്. നമ്മളിപ്പോൾ ഇവിടെ നിൽക്കുമ്പോൾ ഇവിടെ ന്യൂക്ലിയർ റിയാക്ടർ ഒന്നുമില്ല ഇവിടെ അടുത്തൊന്നും, പക്ഷെ എന്നാലും നമുക്ക് ഒരു ഗുഡ് എമൗണ്ട് ഓഫ് റേഡിയേഷൻ നമുക്ക് കിട്ടുന്നുണ്ട്. നമ്മൾ പറയും 2 millisiever per year ഡോസ് നമുക്ക് കിട്ടുന്നുണ്ട്, ഈവൻ വിത്തൗട്ട് എനി ന്യൂക്ലിയർ റിയാക്ടർ എനിത്തിങ് അല്ലേ? പിന്നെ നമ്മളിപ്പോൾ ഈ ഓഡിറ്റോറിയത്തിൽ ഇരിക്കുന്നുണ്ട്. ഈ ഓഡിറ്റോറിയത്തിന്റെ ചുറ്റും ഉണ്ടാക്കിയിട്ടുള്ള ഈ കൺസ്ട്രക്ഷൻ മെറ്റീരിയലിൽ എല്ലാം തോറിയം, യുറേനിയം ഉണ്ട്. അപ്പൊ അതിൽ നിന്ന് ഒരുപാട് എമനേഷൻസ് റാഡോൺ വരുന്നുണ്ട്. ആ റാഡോൺ നമുക്ക് ചുറ്റുമുണ്ട്. ആ റാഡോൺ നമ്മൾ ഇൻഹേൽ ചെയ്യുന്നുണ്ട്. ആ റാഡോൺ ഇൻഹേൽ ചെയ്യുമ്പോൾ ആൽഫ എമിറ്റ് ചെയ്ത് നമ്മുടെ ലങ്സും എല്ലാം ഇറാഡിയേറ്റ് ആവുന്നു. ഇതൊന്നും ആരും അറിയുന്നില്ല. ഇറ്റ് ഈസ് ഹാപ്പനിങ് കണ്ടിന്യൂസ്ലി. അപ്പോ റേഡിയേഷൻ ഫ്രണ്ട്ലി തിങ് ഫോർ അസ്. കാരണം നമുക്ക് നമ്മുടെ ചുറ്റും ഒരു സാധനം. അപ്പോൾ അതിനെപ്പറ്റി പക്ഷേ ഇതിന്റെ പേടി കാരണം, ഇതിന്റെ പ്രധാന ഇഷ്യൂ കാരണം ഈ ബോംബിന്റെ പേടി കാരണം, അതുകൊണ്ടാണ് നമുക്ക് പെട്ടെന്ന് ഈ റേഡിയേഷൻ എന്ന് പറയുന്ന ഒരു തരം ഫിയർ സൈക്കോസിസ് വരുന്നത്. ഇതിന്റെ ഒരു പ്രധാന ഇഷ്യൂ നമ്മൾ ഈ തുടക്കത്തില് ഈ റേഡിയേഷൻ പ്രൊട്ടക്ഷൻ ആൾക്കാർ തന്നെ ഇതിനെ കുറച്ച് പേടിപ്പിച്ചിട്ടുണ്ട്. ആൾക്കാർ ചെറുതായിട്ടൊന്ന് പേടിപ്പിച്ചിട്ടുണ്ട്. കാരണം എന്താ വെച്ചാൽ ഈവൻ ദി റെഗുലേഷൻസ്, ഈവൻ റെഗുലേറ്റേഴ്സ്, our main, the basic principle of nuclear radiation protection is the so-called linear no threshold theory. ഞാൻ അതിനെപ്പറ്റി പറയാം. അതാണ് നമ്മളെ ഏറ്റവും അധികം പേടിപ്പിച്ചിട്ടുള്ള ഒരു പേടിപ്പിക്കുന്ന ഇത്. ഇപ്പൊ ഇന്ന കാലത്ത് പറഞ്ഞ ആളുകൾ ചോദിച്ചു എന്താ ഈ ന്യൂക്ലിയർ പവർ ഇത്ര കോസ്റ്റ്ലി എന്ന്, അല്ലേ? അപ്പോൾ പ്രധാന കാരണം എന്താ വെച്ചാൽ യു ഹാവ് ടു സ്പെൻഡ് എ ലോട്ട് ഓഫ് മണി ഓൺ സേഫ്റ്റി ആസ്പെക്ട്സ്. ഷീൽഡുകൾ വേണം, എക്സ്ക്ലൂഷൻസുകൾ വേണം, വെന്റിലേഷൻ വേണം, അങ്ങനെ ഒരുപാട് കാര്യങ്ങൾ എല്ലാം കോസ്റ്റ്ലിയാണ്. അപ്പൊ അതുകൊണ്ടാണ് ഈ ഇത്രയും ന്യൂക്ലിയർ പവർ ഇത്രയും കോസ്റ്റ്ലി ആവാൻ കാരണം. പക്ഷേ ശരിക്ക് ഈസ് ഇറ്റ് റിയലി നീഡഡ്, ദാറ്റ് മച്ച് ഓഫ് പ്രിക്കോഷൻ ഈസ് റിയലി നീഡഡ് ഓർ നോട്ട്? അതിന്റെ പ്രധാന കാരണം ഈ ലീനിയർ നോ ത്രെഷോൾഡ് തിയറിയാണ്. അതെന്താണെന്ന് ഞാൻ പറയാം. ഏതാണ്? ഓക്കെ, ഓക്കെ, ഇത് ശരി, ഓക്കെ. റേഡിയേഷൻ പോലെ എല്ലാവർക്കും അറിയാം, ഞാൻ കൂടുതൽ പറയേണ്ട കാര്യമില്ല. ആൽഫ, ബീറ്റ, ഗാമ എന്നൊക്കെ കേട്ടിട്ടുണ്ടാവും. ഗാമ പ്രധാനമായിട്ട് ഇലക്ട്രോമാഗ്നറ്റിക് റേഡിയേഷൻ ആണ്. അതിൽ മെയിൻലി നമ്മുടെ വിസിബിൾ റേഞ്ചിനെക്കാട്ടിലും കൂടുതൽ ഫ്രീക്വൻസി ഉള്ള, എനർജി ഉള്ള റേഡിയേഷൻ, എക്സ്റേ, ഗാമ റേഡിയേഷൻ, അതൊക്കെയാണ്. അപ്പൊ അതൊക്കെയാണ് നമ്മൾ സാധാരണ ഈ ന്യൂക്ലിയർ ഇതായിട്ട് അസോസിയേറ്റ് ചെയ്തില്ല. അതിന്റെ പ്രധാന വിഷയം നമ്മൾ പറയുന്നത് എന്താണ്? അയണൈസിങ് റേഡിയേഷൻ. മറ്റേ നമ്മുടെ മൊബൈലിലും ഇതിലൊക്കെ ഉള്ളത് മൈക്രോവേവ് റേഡിയേഷൻ ആണ്. മൈക്രോവേവ് റേഡിയേഷനും ഇലക്ട്രോമാഗ്നറ്റിക് റേഡിയേഷന്റെ പാർട്ടാണ്. പക്ഷേ അത് അയണൈസിങ് അല്ല, അത് നോൺ അയണൈസിങ് ആണ്. ഇപ്പൊ നേരെ വെച്ചാൽ ഈ ഗാമ, എക്സ്റേ ഇതൊക്കെ അയണൈസിങ് റേഡിയേഷൻ ആണ്. അതുപോലെ തന്നെയാണ് ആൽഫ റേഡിയേഷൻ, ബീറ്റ റേഡിയേഷൻ. അതുകൊണ്ടാണ് അത് നമുക്ക് കൂടുതൽ we should be more concerned about that. എന്താണ് കൺസേൺ? കാരണം നമ്മുടെ ബോഡി എന്ന് പറഞ്ഞാൽ കെമിസ്ട്രി full of there are so many chemical, I think 10 to 9 chemical reactions are taking place in our body per second അങ്ങനെ പറയുന്നത്. അപ്പോൾ ആ ഒരു റിയാക്ഷനെ നമ്മൾ ഇൻഹിബിറ്റ് ചെയ്താൽ അത് നമ്മുടെ ലോങ് ടേമിൽ നമ്മുടെ ലൈഫിനെ ബാധിക്കും. അപ്പോൾ അത് ഫോർ എക്സാമ്പിൾ 70% ഓഫ് അവർ ബോഡി, നമ്മുടെ 70% ബോഡിയിൽ 70% വാട്ടറാണ്. അപ്പോൾ വെള്ളം അയണൈസ് ചെയ്ത് എന്താ either it may form H+ and OH radicals, or at least it will form free radicals, OH free radicals. ഈ ഫ്രീ റാഡിക്കൽസ് കാരണം നമ്മുടെ റിയാക്ഷനെ ബാധിക്കാം. അത് ലോങ് ടൈമിൽ can lead to cancer. Of course, body has its own mechanism to prevent that. Okay, next one. Now, radiation measure ചെയ്യുന്ന നിങ്ങൾ കൂടുതൽ ചെയ്യേണ്ട യൂണിറ്റ്സ് എന്താണെന്നുള്ള കാര്യത്തിനെ കുറിച്ചിട്ട് ഞാൻ ജസ്റ്റ് പറയുന്നു. റേഡിയേഷൻ വേഴ്സസ് മെഷർഡ് ബൈ ദ എനർജി അബ്സോർബ്ഡ് ഇൻ ദ മാറ്റർ, ദാറ്റ് ഹൗ മച്ച് എനർജി ഈസ് ഗെറ്റിംഗ് അബ്സോർബ് ഇൻ അവർ ബോഡി. അതാണ് നമ്മുടെ ഇതിന്റെ മെഷർമെന്റ്. അപ്പോൾ ഫോർ എക്സാമ്പിൾ റേഡിയേഷൻ, ഗ്രേ, ഫീവർ ഇതൊക്കെയാണ്. 1 ഗ്രേ ഈസ് നത്തിങ് ബട്ട് 1 joules per kg. അതായത് ഒരു ജൗൾസ് പെർ കെ ജി നമ്മുടെ ശരീരത്തിൽ ചെന്നാൽ അത് പറയുന്നതാണ് 1 ഗ്രേ. It is much less than energy available in a cup of tea. നമ്മുടെ ആക്ച്വൽ എനർജി കണക്കാക്കി നോക്കുകയാണെങ്കിൽ 1 ഗ്രേ ഈസ് much less compared to energy available in a cup of tea. But the difference is that this is iron. That is a difference. Now, ഇത് വന്നപ്പോൾ, അതായത് ആക്സിഡൻസ്, എസ്പെഷ്യലി ന്യൂക്ലിയർ ബോംബിംഗ് വന്നതിന് ശേഷം എന്താണ് ഉണ്ടായത്? അപ്പോഴാണ് ആൾക്കാർക്ക് കൂടുതൽ ഡീറ്റെയിൽ ആയിട്ട് മനസ്സിലായത് ഈ റേഡിയേഷൻ ഡേഞ്ചറസ് ആണ്, ഒരുപാട് കാര്യങ്ങൾ one should be very careful about while handling the radioactivity എന്നൊക്കെയുള്ള കാര്യങ്ങൾ അപ്പോഴാണ് മനസ്സിലായത്. അതിന് മുമ്പ് തന്നെ ഈ റേഡിയോആക്ടിവിറ്റി ഡിസ്കവർ ചെയ്തപ്പോൾ ആരാണ് റേഡിയോആക്ടിവിറ്റി ഡിസ്കവർ ചെയ്തത്? മാഡം ക്യൂറി അല്ലേ? മാഡം ക്യൂറി ഇതിന് ശേഷം അവിടെ ഈ റേഡിയം യൂസ് ചെയ്യുന്നുണ്ടായിരുന്നു ഡയൽ പെയിന്റിങ്ങിന് വേണ്ടിയിട്ട്. അപ്പൊ അന്നത്തെ ആൾക്കാര് ഇതിനെപ്പറ്റി ഒരു ഐഡിയ ഇല്ല. അപ്പൊ ഈ ഡയൽ പെയിന്റേഴ്സ് എന്താ ചെയ്തിരുന്നത്? അവർ ഈ ആ ബ്രഷ് അത് ഇതിന് മുക്കിയിട്ട് അത് ഷാർപ്പൻ ചെയ്യാൻ വേണ്ടി നാവലിനെ ആക്കിയിരുന്നു ആ ബ്രഷ്, എന്നിട്ടാണ് പെയിന്റ് ചെയ്തിരുന്നത്. അപ്പോൾ ആ ഒരുപാട് റേഡിയം ശരീരത്തിനകത്തേക്ക് കയറി ഡയൽ പെയിന്റേഴ്സ്. അവർക്ക് മേരി ക്യൂറി അടക്കം മാഡം ക്യൂറി അടക്കം ഉള്ള കുറെ ആൾക്കാർ ക്യാൻസർ പിടിച്ചിട്ടാണ് മരിച്ചത്. പക്ഷെ അത് ഒരുപാട് ഹൈ റേഡിയേഷൻ, ഒരുപാട് റേഡിയോ അത് ചെയ്തിട്ടാണ്. അപ്പൊ അതൊക്കെയാണ് നമുക്ക് കിട്ടിയുള്ള ഡാറ്റ, ഇൻഫർമേഷൻ, വൈ ഹൗ റേഡിയേഷൻ ഈസ് ഡേഞ്ചറസ്. അപ്പോ ഈ ഡാറ്റയിലൊക്കെ അതായത് സർവൈവേഴ്സ് of the survivors and their projects and the descendants and the next മക്കളും അങ്ങനെയുള്ള എല്ലാ സ്റ്റഡി ചെയ്ത ഒരു വലിയൊരു ഡാറ്റ തയ്യാറാക്കിയിട്ടുണ്ട്. വാട്ട് ഈസ് ദ ഇഫക്ട് ഓഫ് റേഡിയേഷൻ ഓൺ ദോസ്. പിന്നെ പബ്ലിക് അറൌണ്ട് എൻവയോൺമെന്റൽ ഏരിയ അറൌണ്ട് ആക്സിഡന്റ് ലൊക്കേഷൻ ലൈക്ക് ചെർണോബിലാണ് ഒരു മേജർ ആക്സിഡന്റ് ആകപ്പാടെ ഉണ്ടായിരുന്നത്. അപ്പൊ അതിന് ചുറ്റുമുള്ള ആൾക്കാരുടെ എപ്പിഡമോളജിക്കൽ സ്റ്റഡീസ് എന്ന് പറഞ്ഞാൽ is there any effect of cancer on those people? ആ ഡീറ്റെയിൽ സ്റ്റഡി ചെയ്തിട്ടുള്ള ആ ഡാറ്റയുണ്ട്. പിന്നെ നമ്മുടെ കേരളത്തിലെ നമുക്ക് അഭിമാനപൂർവ്വം പറയാം, കേരളത്തിലെ ഹൈ ബാക്ക്ഗ്രൗണ്ട് ഏരിയയിൽ നടക്കുന്ന ആൾക്കാരുടെ സ്റ്റഡി, അതാണ് പിന്നെയുള്ള ഒരു മേജർ ഡാറ്റ. എനിക്ക് പലപ്പോഴും സർപ്രൈസ് വരാറുണ്ട്. ഈ നമ്മുടെ കേരളത്തില് ഏറ്റവും അധികം റേഡിയോ ആക്ടിവിറ്റി ലോകത്തില് കേരളത്തിലാണല്ലോ അല്ലെ? ഏറ്റവും അധികം റേഡിയോ ആക്ടിവിറ്റി ഡെപ്പോസിറ്റ് തോറിയൊക്കെ ഉള്ളത്. പക്ഷെ വൈ വി മിസ്ഡ് ഡിസ്കവറിംഗ് റേഡിയോ ആക്ടിവിറ്റി? അതുകൊണ്ട് അല്ലെ നമ്മൾ തൊട്ടടുത്തുള്ള സാധനം നമുക്ക് കണ്ടുപിടിക്കാൻ പറ്റിയില്ല. അത് ഒരു എനിക്കും അറിയില്ല, അതിനൊരു എങ്ങനെ സംഭവിച്ചതെന്ന് എനിക്കറിയില്ല. പലപ്പോഴും ഞാൻ വിചാരിക്കാറുണ്ട് ഒരു ഫോട്ടോ സ്റ്റുഡിയോ അവിടെ ഉണ്ടായിരുന്നു വിചാരിക്കും. ആ നഗര അല്ലെങ്കിൽ ഡെപ്പോസിറ്റ് ഏരിയ ഒരു ഫോട്ടോ പണ്ടത്തെ ഫീൽഡുള്ള കാലത്തുള്ള അതെല്ലാം എക്സ്പോസ്ഡ് ആവും ഇല്ലേ? തൊട്ടടുത്ത് ഇത്രയും ഹൈ റേഡിയേഷൻ ഉണ്ടാവും. അപ്പൊ ഒരാളുടെ സ്റ്റുഡിയോ അറിയില്ല. പിന്നെ അപ്പൊ അതുപോലുള്ള എന്തെങ്കിലും നമുക്ക് ഒബ്സർവേഷൻ നമുക്ക് ഉണ്ടായോ അറിയില്ല. പക്ഷെ നമ്മൾ മിസ് ചെയ്ത് അത് ചെയ്തതാണ് മാഡം ക്യൂറി. റേഡിയോ ആക്ടിവിറ്റി ഡിസ്കവർ ചെയ്ത് മാഡം അല്ലേ? ഇല്ല, അത് നമുക്കറിയില്ല. അങ്ങനെ എന്തൊക്കെയാണ് നമ്മൾ മിസ് ചെയ്യുന്നത് നമുക്കറിയില്ല. അപ്പോൾ സ്റ്റുഡൻസ് ബി ഫോർ എന്താ പറയാ ആർട്ട് യുവർ ഒബ്സർവേഷൻ. അതിൽ നോക്കുമ്പോഴേ നമുക്ക് അറിയുള്ളൂ എന്താണ് നമുക്ക് മിസ്സാവണമെന്ന് അല്ലേ? ഞങ്ങൾ വാസന്മാരെ ചിലപ്പോൾ ഒരുപക്ഷെ ഞങ്ങൾക്ക് അറിഞ്ഞോളുന്നില്ല. അപ്പൊ നിങ്ങൾ തന്നെ വേണം. പിന്നെ ആനിമൽ സ്റ്റഡീസ്, ഒരുപാട് ആനിമൽ സ്റ്റഡീസ് നടത്തിയിട്ടുണ്ട്. ഈ റേഡിയേഷന്റെ ഇഫക്റ്റ് സ്റ്റഡി അവർ ആനിമൽസിനൊക്കെ കൊടുത്തിട്ട് ക്യാൻസർ ആവുന്നു, ജനറ്റിക് അങ്ങനെയുള്ള സ്റ്റഡീസ്. പിന്നെ തിയറിറ്റിക്കൽ സ്റ്റഡീസ്, ഈ തെല്ല് മാത്രം എടുത്തിട്ട് അത് റേഡിയേറ്റ് ചെയ്തിട്ട് അങ്ങനെയുള്ള സ്റ്റഡീസ് ഒരുപാട് നടത്തി. നമ്മുടെ കേരളത്തിൽ നടത്തിയിട്ട് കൊല്ലത്തൊരു ലബോറട്ടറി ഉണ്ട്, അതിൽ വളരെ എക്സ്റ്റെൻസീവ് സ്റ്റഡി നടത്തിയിട്ടുണ്ട് ഇങ്ങനെയുള്ള കാര്യം. പിന്നെ ഇതിലെല്ലാം കൂടി ഈ ഡാറ്റ ഒക്കെ കൂടിയിട്ടാണ് a huge data collected from the above and were statistically analyzed and resulted in the so-called famous linear no threshold hypothesis. പേടിക്കണ്ട, അത് കുഴപ്പമില്ല. എല്ലാവരും പറയുന്നത് ഞാൻ നല്ലൊരു മനുഷ്യനാണ് പറയുന്നത്. കാരണം എന്താ വെച്ചാൽ ഞാൻ വലിയ ഇക്വേഷൻസ് ഒന്നും എഴുതാറില്ല, പിന്നെ കോംപ്ലക്സ് ഗ്രാഫ് ഒന്നും വരയ്ക്കാറില്ല, പിന്നെ ചോദ്യം ചോദിക്കാറില്ല. അപ്പോ എല്ലാവരും ഞാൻ നല്ലൊരു മനുഷ്യനാണ് എല്ലാവരും പറയുന്നത്. അപ്പൊ നിങ്ങൾ തീരുമാനിച്ചാൽ മതി. ഓക്കെ, ഇതാണ് ലീനിയർ. ഞാൻ റേഡിയേഷനെ പറ്റി പറയുന്നില്ലേ, അതിലും നല്ലത് നമുക്ക് ഇഷ്ടമുള്ള വേറെ സാധനം. എല്ലാവർക്കും ഇഷ്ടമല്ലാത്ത ആരെങ്കിലും ഉണ്ടോ? സ്വീറ്റ്സ് എല്ലാവർക്കും ഇഷ്ടമാണ് അല്ലേ? എല്ലാവർക്കും ഇഷ്ടമുള്ള സ്വീറ്റ്, ലഡു ആയാലും ജിലേബി ആയാലും എന്തായാലും. പക്ഷേ അത് ഡേഞ്ചറസ് ആണ് അല്ലേ? അതാണ് കാരണം അതിൽ ഷുഗർ കൂടും. അപ്പോ ഷുഗർ ഉണ്ടാവുകൊണ്ട് അത് ഡേഞ്ചറസ്. അപ്പോ നമ്മൾ ചോദിക്കാൻ ഡോക്ടറുടെ അടുത്ത് എനിക്ക് എത്ര ഷുഗർ ഒരു
എന്നുള്ള ഈ ഒരു ഇൻഫർമേഷൻ എനിക്ക് കിട്ടണം. അപ്പോൾ അയാൾ പറഞ്ഞു നമുക്കൊരു കൺസെപ്റ്റ് സ്റ്റഡി നടത്തി. എന്താ ചെയ്തത്? 10 ലഡ്ഡു തിന്നുന്ന 100 ആൾക്കാരുടെ ഡേറ്റ, 9 ലഡ്ഡു തിന്നുന്ന ഒരു ദിവസം പെർ ഡേ 100 ആൾക്കാരുടെ ഡേറ്റ, 8 ലഡ്ഡു തിന്നുന്ന 100 ആൾക്കാരുടെ ഡേറ്റ. അതാണ് വയ്ക്കുകയാണ്. അത് ഏകദേശം 1/2 ലഡ്ഡു 1/4 ലഡ്ഡു അങ്ങനെയുള്ള അതുവരെ പോകുന്നു. നമ്മുടെ അത്രയും ഡാറ്റ ഉണ്ടെന്ന് വിചാരിക്കും. ആ ഡാറ്റ വെച്ചിട്ട് നമ്മൾ ഇതിൽ 10 ലഡ്ഡു വെച്ച് തിന്നുന്ന ആൾക്കാർക്ക് ഫോർ എക്സാമ്പിൾ ഒരു 20% ആൾക്കാർ ഡയബറ്റിക്സ് വിചാരിക്കും ആഫ്റ്റർ 10 years. അങ്ങനെ ഡയബറ്റിക് റിസ്ക് ഫോർ ദം ഈസ് 20%. അങ്ങനെ അത് കുറയും തോറും ആ റിസ്ക് കുറഞ്ഞു വരും അല്ലേ? 20% കൂടുതൽ ഉള്ള ആൾക്കാർക്ക് കൂടുതൽ വരും. ബട്ട് ഇറ്റ് ഈസ് 20% ഉള്ളൂ. അല്ല 100 ആൾക്കാർക്ക് 10 ലഡ്ഡു കൊടുത്താൽ 100 പേർക്കും ഡയബറ്റിക്സ് വരില്ല. കാരണം എന്താ? ബോഡി ഹാസ് എ കപ്പാസിറ്റി ടു റെസിസ്റ്റ്. ഇമ്മ്യൂണിറ്റി പവർ ഫോർ ഡിഫറെന്റ് പീപ്പിൾ ആർ ഡിഫറെന്റ്. അപ്പോൾ സ്റ്റാറ്റിസ്റ്റിക്കലി ദർ ഇസ് എൻ ഇഷ്യൂ. അപ്പോൾ ഡിഫറെന്റ് ആയി. മാത്രമല്ല ഈ ഇത് കുറഞ്ഞു വരും. പിന്നെ ഈ കുറച്ച് കഴിഞ്ഞാൽ എന്താ ഉണ്ടാവുക? 1/2 ലഡ്ഡു 1/4 ലഡ്ഡു അവരൊക്കെ ഒരു ഇൻഫർമേഷൻ അവരെ പറ്റിയിട്ട് ഉണ്ടോ ഇല്ലോ ഒന്നും അറിയില്ല. അപ്പോ നമുക്ക് കിട്ടിയ ഡാറ്റ എന്താണ്? ഒരു 5 ലഡ്ഡുവിലധികം തിന്ന ആൾക്കാരുടെ ഡാറ്റയാണ് അതിലുള്ളത്. അത് എന്നിട്ട് അപ്പൊ എന്താ ഈ 1/2 ലഡ്ഡു ഒക്കെ തിന്നാനുള്ള ഡാറ്റ ഉണ്ട്. അതിനാണ് ഇത് റേഡിയേഷൻ ഇതുപോലൊരു എക്സ്പെരിമെന്റ് ആണ്. ആ റേഡിയേഷൻ ഫീൽഡിലുള്ള ഒരു പോയിന്റ് ഇല്ല അല്ലെ? ആ റേഡിയേഷൻ ഫീൽഡിലുള്ള ആൾക്കാരുടെ ഡാറ്റ മാത്രമേ നമ്മുടെ കയ്യിലുള്ളൂ. അതായത് ആ പോയിന്റ് കാണാനില്ല. അതായത് ഇത് ഒരു സൈഡിൽ റിസ്ക് ഫാക്ടറാണ്, വൈ ആക്സിസിൽ റിസ്ക് ഫാക്ടർ, എക്സ് ആക്സിസിൽ ഡോസ്. അപ്പോൾ ഒരു പെർട്ടിക്കുലർ ഡോസ് കിട്ടിയാൽ എത്ര റിസ്ക് വരും അതാണ് അപ്പൊ ഇതിൽ കാണുന്നത്. അപ്പൊ ഇതില് ഈ എക്സ്പെരിമെന്റിൽ എന്താ ചെയ്തതെന്ന് അല്ല, ഈ ഡാറ്റ ഒക്കെ വെച്ച് എന്താ ചെയ്തത്? 100 മില്ലിസിവർ കൂടുതലുള്ള ഒരു എഫക്റ്റും അബ്സല്യൂട്ട്ലി നോ ഇഫക്ട്. 100 മില്ലിസിവർ പെർ ഇയർ കൂടുതൽ ഡോസ് കിട്ടിയ ആൾക്കാർക്ക് എന്തെങ്കിലും ഇഫക്റ്റ് കാണാം. അതിന് താഴെ യാതൊരു ഇഫക്റ്റ്. പക്ഷേ പ്രശ്നം നമ്മുടെ ഈ റിയാക്ടറിന് ചുറ്റുമുള്ളത് നമ്മൾ നാച്ചുറൽ വൺ ഇതൊക്കെ ഹാർഡ്ലി മൈക്രോസിവർ, 2 മില്ലിസിവർ അല്ലെങ്കിൽ 20 മില്ലിസിവർ. ഇതിന്റെ വർക്കർക്ക് തന്നെ 20 മില്ലിസിവർ ഉണ്ട്. അപ്പോൾ 20 മില്ലിസിവറിൽ എത്ര റിസ്ക് ഉണ്ട് നമ്മളെങ്ങനെ അറിയും? നമുക്ക് യാതൊരു ഡാറ്റയില്ല. അപ്പോൾ നമ്മുടെ സയന്റിസ്റ്റ് എന്താ ചെയ്തത്? ഒരു വരയോട് പഠിച്ചു. ആ അവൈലബിൾ ഡാറ്റയിൽ 0 ഡാറ്റയിലേക്ക് നല്ലൊരു എക്സ്ട്രാപ്പുലേഷൻ. അപ്പൊ അതിന്റെ ബേസിസിലാണ് ഇപ്പോഴത്തെ ഇത്. അപ്പോൾ ശരിക്കും പറയാന്ന് വെച്ചാൽ this is not an observed data, this is an extrapolated data. But this extrapolation can be done in different ways. So linear extrapolation is supposed to be the best. At that time regulator must have thought that most conservative, അതായത് ഒരാൾക്കും റേഡിയേഷൻ ഉണ്ടാവരുത് എന്നുള്ള നിലയ്ക്കുള്ള ലിമിറ്റ് ഫിക്സ് ചെയ്യാനുള്ള ഇതായിരിക്കും. അപ്പൊ അതുകൊണ്ട് മോസ്റ്റ് കൺസർവേറ്റീവ്. പക്ഷെ ഇപ്പോൾ അത് അന്നത്തെ കാര്യം. കാരണം ഈ ഇതൊക്കെ വന്നതിന് ശേഷം ന്യൂക്ലിയർ ബോംബിങ് ഇതൊക്കെ കൂടുതൽ ഡാറ്റ ഒന്നും അവൈലബിൾ ആയിരുന്നില്ല എന്ന്. പക്ഷെ ഇന്ന് കാര്യങ്ങൾ ചേഞ്ച് ആയി. ഇന്ന് നമ്മുടെ ഒരുപാട് ഡാറ്റ അവൈലബിൾ ആണ്. എംപ്ലോയീസിന്റെ ഡാറ്റ അവൈലബിൾ ആണ്, ഹൈ ബാക്ക്ഗ്രൗണ്ട് ഏരിയാസിന്റെ ഡാറ്റ അവൈലബിൾ ആണ്, നോട്ട് ഓൺലി ഇൻ ഇന്ത്യ, ഓൾ ഓവർ ദ വേൾഡ്. അപ്പോ വൈ നോട്ട് വി തിങ്ക് ഓഫ് റീവിസിറ്റിംഗ് ദ LNT തിയറി? അതാണ്. അപ്പോൾ ഈ LNT തിയറി റീവിസിറ്റ് ചെയ്യണം എന്നുള്ളതാണ് ഇപ്പോ പുതിയൊരു ജനറൽ തിങ്കിങ്. അപ്പോ ഈ നമ്മൾ വേറൊരു തരത്തിൽ ഇതിനെ എക്സ്ട്രാപ്പുലേറ്റ് ചെയ്ത ഈവൻ ഓർമോസിസ് ഇഫക്ട് ഹരിദാസൻ പറഞ്ഞു, there is likely to be some positive effect of radiation. കാരണം നമ്മുടെ എർത്തിലുള്ള ഏത് കാര്യങ്ങളും നോക്കിയാലും ഒരു ഡെഫിഷ്യൻസി ലെവൽ, ഓപ്റ്റിമം ലെവൽ, ടോക്സിക്. ഏത് സാധനം എന്ത് സാധനം എനിത്തിങ് അണ്ടർ ദ സൺ. കുറച്ച് ലഡുവിന്റെ കേസ് പറഞ്ഞ പോലെ നമ്മൾ ഈ കാർബോഹൈഡ്രേറ്റ് വളരെ കുറഞ്ഞെന്ന് വിചാരിക്കാം. അപ്പൊ ഇതേ ഈ ലഡുവിന്റെ കേസിൽ നമ്മൾ എക്സ്ട്രാപ്ലേറ്റ് ചെയ്ത് തരുന്നത് വെച്ചാൽ ഈ ഒരു തരി ലഡു പോലും ഈസ് ഡേഞ്ചറസ് എന്നുള്ളൊരു ഇതല്ലേ വരിക. ബട്ട് ഇറ്റ് ഈസ് നോട്ട് കറക്റ്റ്. അത്ര ലഡു കഴിച്ചില്ല അല്ലെങ്കിൽ എത്ര ഷുഗർ നമ്മൾ കഴിച്ചില്ലെങ്കിൽ നമ്മള് ഷുഗർ പ്രോബ്ലം വരും അല്ലേ. അപ്പോ you should have some optimal level should be. Same case with the radiation. The natural radiation is already there with us. Okay. അപ്പോ ഈ സ്റ്റഡീസ് നടത്തിയത് എന്താണെന്ന് വെച്ചാൽ നടത്തിയപ്പോ ഫൈനൽ റിസൾട്ട് എന്താണെന്ന് വെച്ചാൽ വർക്കർക്ക് 20 millisieverts per year ലിമിറ്റ് വെച്ചു. ജനറൽ പബ്ലിക്കിന് 1 millisieverts per year വെച്ചു. അപ്പൊ ശരിക്കും നോക്കാച്ച ഈ ലീനിയർ ഫ്ലോ ത്രെഷോൾഡ് തിയറി ശരിയാണെങ്കിൽ നമ്മൾ വർക്കേഴ്സിന്റെ ക്യാൻസർ around 60,000 people DI people ആൾക്കാരുണ്ട് നമ്മുടെ ടോട്ടൽ ഇന്ത്യ. അപ്പൊ അവരുടെ ക്യാൻസർ റേറ്റ് സാധാരണ ആൾക്കാരുടെ കൂടണ്ടേ? മാത്രമല്ല നമ്മുടെ ഹൈ ബാക്ക്ഗ്രൗണ്ട് ഏരിയയില് around 18 millisieverts per year കിട്ടുന്ന ആൾക്കാരുണ്ട്. അപ്പൊ അവരുടെ ക്യാൻസർ റിസ്ക് കൂടണ്ടേ? അപ്പൊ ഇത് രണ്ടും സംഭവിക്കുന്നില്ല. അപ്പൊ അതിന്റെ അർത്ഥം എന്താ? ഈ ലോ ലെവലില് ദിസ് ഈസ് നോട്ട് അപ്പ്. ഈ LNT തിയറി ഈസ് നോട്ട് അപ്ലിക്കബിൾ. So one has to go for a better theoretical studies. So for that a lot of data is generated and I will not go deep into that. So what I wanted to say is there is a need for revisiting the LNT theory. And this is very important for a nuclear person. As a radiation protection man, I should get first educated on this. Then only I can teach the general public, so that common fear can be completely avoided. അപ്പോൾ ഈ പറഞ്ഞ കൂടുതലുള്ള ഇഷ്യൂ, അതായത് ഫിയർ സൈക്കോസിസ് ഫോർ റേഡിയേഷൻ completely ready. So I have to stop. So these are some of the data. I will do one thing. If somebody is interested, they can come back and ask me. A lot of data is available with me. I will not go into this risk analysis, Chernobyl reactor, cellular studies, and then cancer treatment in low-level radiation, effect of cancer, and then risk of death among children of survivors. There's large volume findings. So finally, what I want to say, this is definitely time to have a relook of the cornerstone concepts of radiation protection philosophy. In fact, this concept has led to more deaths than preventing virtual deaths. It is good the argument that recent times opinion is building up around the globe, all over the world, by the authorities in India also against the LNT, and there is a need for further understanding the risk due to low-level radiation. So even ICRP has told that you should not use the risk factor calculated on the basis of LNT for extrapolating the cancer risk. Here is പ്രത്യേകം പറഞ്ഞിട്ടുണ്ട്. പിന്നെ okay, I will not do. So I think I will finally I will conclude like the LNT does not take into account the organism. The main reason why this LNT obsolete, mainly because it doesn't consider the immune system capacity of our own body to resist the biological recovery time between the dose and dose rates. That also is an issue. Because whatever LNT is based on a very high dose rate, but what we have is very low dose. Other relevant mechanisms that operate at low doses from actual organism, then in the experimental study versus the epidemiological study, biological information will have a large redundancy. It is not considered in the LNT. And cancer is now it is understood that cancer is a multifactorial condition. Cancer radiation is not the only thing. Smoking is there, malnutrition is there, chemicals are there, so many other things are there. So radiation may trigger, but the 30%, the natural cancer risk is 30%, but the radiation contribution to radiation are hardly less than 1%. So you will not even able to understand whether there is an effect of radiation at all. So there is a research needed to understand this, and also the effect of hormosis also has to be studied. I think I will stop it because I have so many other slides also, but if anybody is interested, they can contact me. So thank you very much once again for giving me this chance. ആർക്കെങ്കിലും ചോദ്യം ചോദിക്കാനുണ്ടെങ്കിൽ മലയാളത്തിൽ ചോദിക്കാം. അല്ല ഇപ്പോഴല്ല ചോദിക്കുന്നത്, അത് പിന്നീടാണ് ചോദിക്കുന്നത്, അപ്പോഴും ആവോ, കുഴപ്പമില്ല. ആർക്കെങ്കിലും എനിക്ക് മനസ്സിലാവും, കാരണം ഇത്രയും ടയേർഡാണ് ആൾക്കാർ. പക്ഷേ ഇനി ചോദ്യം ചോദിക്കാനുള്ള കഴിവൊന്നും
Thank you, sir. We had a truly inspiring session. Now it's time to express our gratitude. I would like to invite Sree M. Bhaskaran, sir, to give a present, a memento and a book titled On the Wheels of Education, Serving USA and India, written by Professor Sree Krishna, a renowned scientist, to Dr. P.M. Ravi, sir. Sir, please. Now, to honor Sree M. Bhaskaran, chair of the session, and Dr. Manu K.M., co-chair of the session, let me invite Sri K.K.P. Nair, Secretary, AIRA. As we conclude on the first day of this symposium, I would like to express my sincere gratitude to each of you for the active participation and enthusiastic engagement. We look forward to welcome you back tomorrow for another day of enlightening session. Be back at tomorrow 9:30 p.m. 9:30 a.m.